Hello everyone, my name is Elena Gonzalez from MDPI and I will be the host today. Welcome to the third live session of the 8th International Electronic Conference on Sensors and Applications. This conference is hosted online from 1 to 15 November 2021 and it is organized by MDPI and the journal Sensors. During this time, the conference presentations will be available for discussion on the conference website. And all accepted proceedings papers will also be available in the journal Engineering Proceedings. Furthermore, the journal Sensors will publish a special issue of the conference proceedings papers. I would like to thank the conference chairs, Dr. Stefano Mariani, Dr. Alberto Ballan, Dr. Stefan Bosse, and Dr. Francisco Falcone, along with the conference committee for making this conference possible, and all speakers, and of course, our attendees that are joining us today. I would like to remind everyone that this live session is being now recorded, so we will post the recording soon at the conference webpage. Today's session is also being live streamed in YouTube, so hello to those ones that are watching us on there. Today we will have one keynote speaker presentation and 10 presentations from the student session. The presentations will be followed by a Q&A session to answer any questions submitted by live online audience. So if you're joining us live, please type your questions in the Q&A box that is below your screen, and mention the name of the speaker to whom you address your question. Finally, the session chair for today's lecture is Dr. Stefano Mariani, who is an associate professor at the Department of Civil and Environmental Engineering of the Politecnico University of Milan in Italy. Thank you, Stefano, for chairing this session. I'm handing over the microphone to you, and every one of you enjoy.
Thanks, Elena, for the introduction. So it's a very pleasure for me to be here chairing this session today. So today we have a very tight schedule. First of all, we have the keynote speech by Professor Giorgio Sberveglieri. And next we will have the student session. So I hope you will enjoy all the presentations today. So I would say without much ado, I will start by introducing Professor Giorgio Sberveglieri. I will say really a few words to Giorgio to let you have as much time as possible for your very interesting talk. So there will be much to say about Giorgio, but I would just try to summarize by saying that he graduated in physics at the University of Parma. Then he moved to Brescia, where he's still a professor there. And the most interesting thing to notice is that in 2016, he was co-founder of a startup whose name is Nano Sensor System. And they work in developing very interesting stuff regarding electronic noises and so say chemical sensors. So I stop here, and Giorgio, I say thanks. It's very much appreciated that you to be here to deliver this keynote speech today. Thanks for joining us.
Thanks, Stefano, for introducing me. I would like to thank the conference committee to invite me to show the result of obtaining our spin-off company, also in the university, about the chemical sensor. Then today, my talk will be mainly about the evolution of metal oxide sensor applied to electronic nodes. Just a few words about the chemical sensor. Not all the people able to understand very well. This kind of device is a device that transforms the chemical information, ranging from concentration, some specific component, by the electronic nodes mainly to total composition analysis. And the chemical information may originate from chemical reaction analyzed or from physical property of the system. And nowadays, also in the past, the main application of the sensor was to use the solid state gas sensor. And that's another name. Some people claim chemical is more broad in meaning. Instead, gas sensor is the more devoted sensor for the electronic nodes. And just information, because also in the very important paper, there is some confusion between the response and sensitivity. Sensitivity is the derivative of the output signal respect to the concentration of the analyte. Is the derivative of the signal respect to the concentration. You can see in this figure, for example, that in this case the sensitivity is 0. Instead, the response, the relative change of the resistance, is very high. Then has two different meanings. Some people reporting the paper sensitivity or response don't understand very well the difference. For example, you can see here, in order to have the information about detection limit, the best method to me is to have the derivative in the low point of the response. And you can see moreover that in this case, the derivative change depending on the concentration. For example, in this point, if you have a change of the concentration exactly increasing or decreasing, you can see the signal is not the same, change completely. That is important because, repeat, in several papers, there is a confusion about that. Let's me to come back that at my talk of today. Then the sensor for electronic nose could be classified depending on the variable parameter. For example, if you change the work function, we have a ChemFET, MOS, Kelvin probe, lapse, or change in the conductivity. That is, my talk today is mainly focused on this one. But the change of the mass, for example, where it's surface acoustic wave or quartz microbalance, or optical properties of the device can be taken in account. That is, we have different type of the material. It is another figure that can show the gas sensor for the electronic nose can be classified in optical sensor, like fluorescent, reflective, absorption, thermal, mainly the list of also other devices today, electrochemical. In the electrochemical, we can include also the metal oxide semiconductor. It's the focus of mine today in this area. Gravimeter, that surface acoustic wave told you, or other kind of device, and also the biosensor applied to electronic nose. About the metal oxide semiconductor, the advantages of metal oxide semiconductor, such as cross sensitivity, broad spectrum resistance, stable performance, low cost, that are therefore the most applied in the electronic nose. And several company or other university group or laboratory, very famous laboratory, use commercial metal oxide gas sensor, might be produced in China and Japan. Other company like my spin-off, we have the tailor-made gas sensor. And we will include also, since there is sensitivity of the gas sensor, also temperature of the air enter inside the chamber of the sensor. We need also temperature sensor, humidity sensor to include, and that usually are commercially available with low cost. Then, as I told you, we study mainly the conductivity change or impedance, depending on the case of this device. I told you the metal oxide semiconductor, they have a reversible redox process of the analyte gas company. Some other people also the semiconductor sensor, but organic have a great advantage respect to metal oxide for the selectivity. Sometimes it's not so stable or the drift is higher than respect to the semiconductor metal oxide. Also in the past, carbon nanotubes. Very recently, some laboratories introduced the graphene-based gas sensor. One of the big problems that we have in the sensor, more or less in all kinds of sensor, is the sensor drift. It is a challenging problem in the chemical sensor of electronic nose machine. In which way we can reduce the sensor drift? One way that uses also me is to have a pre-aging of the gas sensor. Then in order to have a very stable, to maybe heat in some temperature, in order to stabilize, or to have a structure of the grain size, very nanostructural. When the grain size distribution is not so large, then we have maybe only a not large difference of the grain size. Sorry. Another method is to use a pattern recognition approach, like artificial neural network or other tools to solve an input discrimination problem. In order to have maybe reduce as much as possible the sensor drift for a long time, maybe for 1 year, we can use the sensor without to use change or make other kind of modification. Sorry. Then I told you the Internet of Things is very important. It's important. Why? Why? Because we will show you later that the design of the sensor are sent in cloud. In cloud, we use Internet of Things. And Internet of Things is very important because inside that we can have the pattern recognition method, we can update, we can consider also the drift of the sensor. Moreover, there are other kind of important activity inside the Internet of Things. For example, data, big data acquisition, remote control of the electronic nodes, data storage, and so on, advanced statistical tools to do like artificial neural network or otherwise, and the pattern recognition method. Then the big difference between the old type of the electronic nodes and the new one is in Internet of Things. Because in the past, I will show you later, there was not this possibility. Why? Why? Because in the past, the electronic nodes was maybe 30 years ago, produced and produced by a company or in the university. There was not at that time the possibility to have a software. I'm sorry again. The electronic nodes is typically composed by 4 parts. One is the sampling system. Sampling means introduce the gas inside the electronic nodes. Then there's an array of sensors. In the red, I've reported the activity nowadays in several laboratories. Sampling system instead is commercially available. Like this one we show in our laboratory is an autosampler. This autosampler is mainly used for having the big data. We have 42 vials. Inside we introduce the analyte. Then we make in very short time, you obtain a very big data. It's important for the processing unit. Array of sensor, what kind of sensor we need? It's not important to have selective. Sometimes we don't need selective because we need to consider the broad spectrum of the analyte, but they have to be stable. It's important to have a very low drift and reproducible one. Then the electronic circuit could be commercially available. There is no big activity, it's not innovative, this one. Instead, we have the information process unit, like vector machine or artificial neural network. We are working mainly in gas sensor information process unit. Not only me, but the several laboratories around the world, we focus activity mainly in 2 different parts. Okay, about the application. There's a broad application. The electronic nodes start to study and to produce about 35 years ago. At that time, was not very good electronic nodes. And nowadays, we have very new electronic nodes with great performances. Then we have discovered a lot of application of this kind of device. Mainly is for example, air quality system, ripening, alcohol test, freshness of food, I don't know, toxic agent, indoor air quality, medical diagnosis, artificial infection. As I told you, I will show you later something about the Internet of Things. Is very important in order to solve some problem, mainly to update the algorithm, for example, or to avoid the drift of the sensor. Okay, that concerning the metal oxide semiconductor, we have a network usually of that, cost effective, and are applied mainly at the moment of the food safety. We start to use also, they start in driverless car. Artificial infection is very important. It's connected with the Internet of Things using big data. We need both of them, big data and Internet of Things, of course, to have a very good electronic nodes working perfectly. As I told you, the first version of the electronic nodes was started about around 40 years ago, more or less. And that was very important in this case. To have some input gases, some chemical sensor, and then the electronic circuit. And then the pattern recognition was a very complete device. There was a big problem in 2 points. The sensor was not stable, scarcely reproducible, and the pattern recognition was directly fixed directly on the instrument. This was the main motivation because the first version of the electronic nodes doesn't work so much. It was not successful, really not successful. But in the last 10, 20 years, the situation changed. That the new version of the electronic nodes, like in our electronic nodes, the other one on the market now, is that we have the most stable sensor. The stability is increased a lot in the last years, and an auto sampler that in order to have the big data in the cloud. And then we have a web app in the cloud. That is very important. Both of them are really important. Sometimes the people on the companies or the final user are not interested in the algorithm. They are interested in the auto signal. Sometimes in the practical application is enough in the like a light switch to have green, red, or yellow to understand that it's good material. The food sample is perfect. There are big problems, might be contaminated by bacteria or other time, mold, and so on. And maybe in the yellow instead, there is a problem. That is the new system, used a lot. And as I told you, we are mainly working in the web app and in the sensor chamber. Nowadays, there are several data applications already on the market. And in the future, we'll find this kind of application also in domestic application in large area. About the sensor, at the beginning, about 30 years ago, 40, the sensor, metal oxide sensor, were mainly thick film. I'm sorry, it's not high resolution. I was taken from a very famous paper of Professor Goper. Then is that was used a lot. Standard method and so on, but the problem was mainly, as I told you, the low reproducibility and the drift of the sensor. Was really very low cost, no probable cost, but the problem to have a very good result. After the thick film, maybe, I don't know, 20 years ago, more or less, some university and other companies start to use thin film technology. Also in my laboratory, we use a thin film technology, but the situation was not increased a lot, better sensor, more stable, but they don't solve completely the problem to have a good sensor for the electronic gnosis. And the situation changed dramatically about 20 years ago, because 20 years ago, there was the first paper published by myself, my team, and the group team, Professor Zolli Wang, about to use the nano wire. At that time, we call nano bells because it seems to be bells, not wire, but the change that really we changed. We demonstrate for the first time was possible to prepare the same material, same semiconductor oxide, exactly the same, use it first in the thick film technology, then in the thin film technology, and we verified that that increased a lot the stability. Why increase the stability? Because this kind of material was grown, we show later a few slides about that, was grown at very high temperature, maybe 800 degrees centigrade or 900 degrees centigrade. That was really very good crystalline property. Sometimes we was able to prepare the same material like tin dioxide in single crystal. Nano belts like this one, single crystal, flexible, because the property at nano level changed completely respect to large grain size. In this case, that was surprising. Very good stability, short time of response, and we demonstrate it was possible to produce that in very simple manner. The structure of the sensor with the nanowire was not so much different respect the thick film or thin film technology. More or less is this one. We have substrate using alumina, but some people also use maybe other kind of insulating and mechanical stable material like glass or recently also quartz. And in the back side, there is a platinum heating element. The platinum heating element is very important in order to have the good control of the temperature to heat like a micro oven, like small oven, and at the same time, to have the control of the temperature. We are able to guarantee exactly the working temperature is the same. Also say change the room temperature, maybe from 0 degrees centigrade or 40, is not important. Remain exactly the same, because you know probably that if you change the working temperature of the sensor, we change the response, of course, of the sensor. Then on the other side of the alumina substrate, there are the platinum interdigit electrode usually, and maybe you can see here the nanowire. That's exactly the same. Only difference between this kind of structure and the previous thin film is only the sensing layer. The sensing layer, and what could be made, for example, the most popular is tin dioxide, also zinc oxide. And we show you that there are also other kind of technologies. Then the final device is this one. You already see here that we are working other kind of material, not only tin dioxide. That is material suspended. The side, lateral side, usually about 1 for 1 millimeter square, 2 for 2 millimeter square, more or less. This is the range of the size of this kind of device we are able to produce in our laboratory and in other kind of laboratory. Why the metal oxide and why for chemical sensor? Just a few words about that, because we have a very large surface to volume ratio. The downsensing material improve the sensor performances. Why? Because the dimension of the nanowire is comparable with the surface charge region. Then we can move that very easily. And that is why we have a very good response in the metal oxide together with the stability. The stability, why? As I told you, because we have a high degree of crystalline order. In order the metal preparation method, we show you maybe one in our spin-off, is very simple. And also we can increase the selectivity using the surface functionalization by catalyst, for example, or other method. Then, as I told you, we are using different methods of preparation. The most important for us is the method of the bottom-up. Then instead to use top-down, it's possible. Some paper demonstrate it's possible to use to obtain metal oxide semiconductor, starting with technology of semiconductor industrial. But that is very expensive and the process is really slow. We prefer to use the most close to a practical application is the bottom-up method. The advantage is high purity and crystallinity, small diameter, low cost, and we can make doping or junction, PN junction in the sensor. The disadvantage is to have the transfer to planar surface could be some electrical contact sometimes is a problem, but we are solved this kind of problem. Then the method used for synthesize the metal oxide semiconductor in form of the nanowire are either physical based method, for example, physical vapor deposition, electrospinning, pulsed laser deposition, or we can use the chemical based method. There are a few examples that we obtain in our laboratory is the chemical vapor deposition, thermal oxidation, hydrosolvothermal growth, salt gel synthesis. We have prepared a long list of material to verify what is the best for the application. I have no time to show all the application today, but it's clear then if you like to obtain a tailor-made sensor for some specific application, we have to change the material and the algorithm or the pattern recognition method, both of them. Then we decide to prepare a long list of material like zinc oxide, titanium oxide. Also, for example, copper oxide is a P-type material because in some time for some application, it's also very important to use a P-type material, not only N-type, use up to now. Just a few words about the method of we grow that in our laboratory. It's not a new method. Wagner Ellis in early 60s already used this kind of method. This kind of method is used not only for metal oxide semiconductor, but also for carbon nanotubes or other kind of material. We can divide this method in two different techniques. One is vapor solid mechanism. The other one is vapor liquid solid mechanism. I can show here, and you can see very easily. Then when we use the liquid solid, we are first to deposit the metal catalyst, use with gold or other kind of catalyst. Then at the temperature, we have the liquid droplet when we deposit tin oxide. Then there is a super saturation and growth of that, and we obtain a nanowire. The second one, instead, in some condition, we can deposit only the material. We have the nucleation, seed formation, nucleation, and grow nanowire. Honestly speaking, we prefer the first one, the vapor liquid solid, because in this way, we can deposit metal catalyst in some defined area on the substrate in order to define the area where grown the nanowire, not in other area. Then this is the best method to me because we can deposit, not so difficult to deposit noble metal like palladium, gold, or ruthenium in by sputtering, for example, in order to have a very good device with low area in indefined area. Then is just an example of the furnace that we are using. In this case, there is a very advanced method. There is a gas inside. There is inside the area, high temperature area. Then inside there is the substrate. there is the gas to enter. And typically in this case, in the center, there is a low distance between the powder, the material, and the substrate. There is a transportation method of that, the very easy method to prepare this one. All the parameters are very well controlled. They are important, this one. For example, the pressure control, temperature control, mass flow controller, vacuum pump. If we control all the parameters, in this case of the furnace, we are able to have a reproducible sensor for electronic nose application. One drawback could be that the area is not so large, that we can grow maybe in the same time, maybe 20, 40, not thousands of sensors. Then for obtaining thousands of sensors, maybe we have to change the furnace to the largest one. I verified that in the US, close to New York, you remember, there is a company able to produce this kind of furnace for very large area, metal oxide, nanowire grown. Then, as I told you, we need to control very well the parameter in the tubular furnace. Important the substrate temperature, also the time, because in the time grow more or less, that will control very well to obtaining the reproducible chemical sensor with a nanowire structure, as I told you, very stable and very reproducible. These are a few pictures about the sensor developed in our company. Depending on the application, we can use, for example, in this area, we verify there is only mechanical protection. There is no other kind of protection. Depending, if you have powder, for example, in the area, it's better to introduce maybe a mechanical filter. And then you can see here, there is the preparation of that. You can see there is the interdigitated in clear. In dark, instead, you can see here is the nanowire. It's a good sensor with the good properties, ready for apply in an array of sensors, of course, in the electronic nose. But in the last 20 years, grow a lot of the new nanostructure. This is just a picture. You can see here, maybe the name changed because the name is flower, I don't know, sheet, o-ring, and so on. Different kind of name that are important because it's like the nanowire, but maybe are more easy to prepare, different properties. The best solution for that is to use the structure with high level of crystallinity, because I remember that the working temperature of this kind of sensor is usually ranging from 300 degrees centigrade and 500 degrees centigrade. Then if the material is not a single crystal or with good crystallographic properties, is not stable. Then in any way, the different laboratory, they use different kind of the nanostructure, like the nanocubes and so on. If you are able to have a good structure like this one, the surface area increase a lot. This is important. Then we decrease the the limit of detection. And in that case, also maybe this structure, for example, like a tree, we have the diameter of the nanowire, the nanostructure very low. That means that the response is very high because we have completely change of the conductance in this kind of area. And the second one is the response speed increase a lot. Then is a new class of material. There are several papers in this area. In the case of the metal oxide, they're really promising for obtaining new kind of the electronic nose with this kind of structure. That is really recently activity in the last 5-10 years, no more. Then I expect then that could be applied by companies in Europe or Japan, Asia area, or in US for obtaining new kind of the electronic nose and applied for domestic application also. In the fridge, for example, I remember that I know that some large company in US are using this kind of method to introduce on the market the gas sensor inside the fridge, in order to control the food inside the fridge. Or other company are like in Korea, they are using this kind of material and the structure to control in the oven, domestic oven, the cooking of the food. Then there is a plenty of material. We are at the beginning of the new era of the metal oxide applied for very large scale. I expect in a few years that will be on the market maybe thousand, or maybe million of the electronic nodes, very simple, that are using this kind of structure. This is a figure taken from a colleague of the Korea, and at the beginning was mainly tin dioxide, as I told you, in my laboratory in the several university about 20 years ago. Then we moved zinc oxide nanowire or like that, then titanium dioxide, and we can show here in the very short figure, not so large information, but in this case, when you end material, the oxygen is outside. When there is a reaction, change the surface area and is more increase the resistance, then decrease or increase the resistance depending of the gases arrive. A new type was very recently in the electronic nodes. They are using p-type. Mainly, they are using the nickel oxide or copper oxide. Also recently, some other new material like cobalt oxide and so on. The p-type usually doesn't respond like in n-type. The response is lower, but it's important for some application to detect some gases that are not detected by n-type material. Then, to me, I believe the best array for sensor for the electronic nodes is to use n-type together with the p-type material. This seems to be our very good solution for that. Okay, for example, in our laboratory, we have used nickel oxide, is a p-type. When using nickel oxide toward nitrogen oxide, you can see here the response is really good. And we increase the conductivity because usually in the p-type decrease if we have the oxidizing or reducing gases, but with oxidizing gases, the gas increase. That is one of the examples together with the calibration curve depending on the concentration. You can see here that a concentration, really low concentration. For example, in nitrogen dioxide, is we are able to detect very easily by, I don't know, 2 ppb. That is very important. 2 or 20 ppb, depending on the application. Okay, about the nano system, I would like to conclude my talk, give you about information about our team, the team of why in our company, in our spin-off of University of Brescia. We have several PhD from University of Brescia, University of Modena, Reggio Emilia. This is the name of the people. About the metal oxide gas sensor in our electronic node, you can see our new electronic nodes. There is a large display, monitor, touch screen. We can control everything, for example, temperature, sorry, it's in Italian, temperature, the sensor, the humidity, the flux, the temperature, and so on. We control everything. Of course, that is online. And we use, I told you, metal oxide gas sensor or sensor prepared by thin-film technology. RGTO was discovered by me 30 years ago. And recently also we tried to use, not reported here, also the technique of the thick film to maybe different kind of technology, nanowire, thin film, and thick film together. Seems to be winner this solution for different application. About the field application, I told you there is a large application nowadays, mainly in environmental, like indoor, outdoor, water control, plastic, all of the recycled plastic, food from farm to fork, like geographical identification, brand identification, and microbiological or chemical contaminant. Then in several laboratories try to use this kind of sensor. Also in my university and in my laboratory, smart open home, but it's confidential. Then health, in order to assist and control the home, maybe for 24 hours a day. That is a new application. Some people try to apply also for health, considering the type now that the people stay at home with COVID and so on, with the pandemic. We have to control the heat at home with some specific sensor. Okay, just another list, but more or less is the same as previous. Then we mainly work in monitoring the microbiological contaminant like yeast, bacteria, molds. We are using air pollution control, geographical identification, assisted in certification, purification process, that we are using that for really a large broad of the application. I would like to conclude then, and from this very short overview of the metal oxide sensor, and my idea is that the new type of structure of nanometal oxide sensor, either p-type, n-type, or heterojunction is another possibility, are the best candidate for the new electronic series as the market expects. And the market, there is a little expectation from the market because they are waiting that kind of electronic nodes to solve several problems. Thank you a lot for your attention.
Thanks, Giorgio. Thanks for a very nice and interesting presentation. Now we are open for the discussion. So we have, I would say, plenty of time for asking questions regarding technology, applications, and whatever to our keynote speaker. So should you have any question, either if you're allowed, you can raise your hand and I will give you the word, or otherwise you can write your question in the question and answer box. So in the meantime, Giorgio, I will start asking something. So out of curiosity, maybe my questions are not really to the point, but just to start with them. So you mentioned the application of machine learning in order to discriminate, to do identification, classification, clustering, whatever. And you said that in your sensors, you typically do on the cloud. So you have an app and you do on the cloud. So I guess that because of the connection to the cloud, so you have a bit of power to be devoted to this. And so question is, if you do something embedded, you know, there's a lot of work currently done on neuromorphing computing. So and so the idea of going down and to do something not with software anymore, but doing with the hardware. So do you see any connection between these two different words and the possibility to make a new market even more?
Yes, it's true that there is both interest in two different methods. Mainly, the most important to me is to use in cloud to send the data, because in that case, for example, we decide now to use the Microsoft Azure platform, and the Microsoft give you also several algorithms ready. You pay maybe a fee every month. You can change. You don't need to be a good scientist in this field because they support you in a very, very easy way. That seems to be the better one to start, maybe to have a good sensor, to verify what is the best algorithm. But in some cases, for example, some company asked to me to use the embedded state, all the algorithm inside, mainly for protection. Or maybe you are able to send, I don't know, the sensor and the electronic nodes in area not well covered by Wi-Fi or by internet. In that case, in which case you are not able to use the cloud system. Then both of them are very interesting, depending on the application, of course. To me, in the laboratory, for starting, it's better to use the in-cloud. My other company that, for example, they produce domestic application. I don't know, some domestic, but in area, maybe in Asia or in, I don't know, in Africa or in other place, in some people, they are no internet. That's why they would like to use this one. In other words, when you have defined exactly what is the pattern recognition method, we can put this kind of pattern recognition method inside directly at the device. Then it's not so difficult, of course. Sure. It's true. Both of them survive. Both of them have a future. Sure.
Okay. Thanks. Thanks. Any questions? If not, I move on. I have a few. So, concerning the health applications. So we hear every so often that they are going to introduce these kind of sensors in our cell phones. So there are some brands typically showcasing probably their products to say that they're going to introduce. Is there anything already available there? And in case, what's the quality of this type of sensors already included in comparison to yours, for instance?
But there are some companies, very large company. I have in mind the Siemens company, for example. We are working together in European project financed by European Commission to include directly on the sensor on the mobile phone directly an external device connected directly on the backside of the mobile phone, and for asthma detection. For asthma, that is very important. Okay. This one because the people that have asthma, they have to take too much chemical compound. Sometimes it's not important. Seems to be many psychological activity, not really, they don't really need. And then promise me that we'll enter in the market very soon with this kind of sensor. One of the problems was the power consumption, because the power consumption sometimes is a problem. And they are using maybe very low power sensor, but very low power usually is not so stable. Then it is in discussion the method. I don't know, several companies are working to use the mobile phone directly, connected directly, or in other case, like the people that are using some health problem to use only the web app, only the app on mobile phone connected by Bluetooth with external device. There are two possibilities. One external device directly on your body, for example, to detect the glycemia, or the other kind of the problem. They send the data by Bluetooth directly on your mobile phone. Your mobile phone send the data to the medical doctor, or then that is the other possibility, especially now there is the lockdown for COVID and so on, and the people have no time or not possible to go to the hospital. They have to stay at home. There's a great activity in several companies, mainly US, I believe, to develop new kind of device to detect some health problem when you stay at home. And that is a lot of them. And then maybe very soon they will be on the market in this way, because and the people, they would like to reduce the cost, not going to the hospital, because in the hospital is very costly, of course. You have to move. Instead, if you stay at home, and the medical doctor or the hospital can control directly your problem, like, for example, to do asthma or the other one, they can give you maybe information, maybe, okay, you stay very good, no problem. It's only psychological problem. It's not really a health problem. Sometimes happen because when the people is at home for days and days, lockdown, what happened? They believe to have some problem. Is not true. The medical doctor can control directly your health. This is a great activity also in this area. Sure.
Okay. Yes. Yes. Thanks. No, because so probably again, it's a matter of psychological issue, but so the main application can be, so for instance, because you typically breathe into your cell phone, so they say that it will be possible to detect early breast cancer, and that would be extremely important, because for instance of air pollution we typically have in our cities, and so I think there will be an extremely important market for this kind of chemical sensors in case you can have a kind of capability just embedding everything into your cell phone. Yeah. Okay, thanks Giorgio. So I see we have a couple of questions. So Elia, please.
Thank you. At first, thanks for the real great presentation, Professor Sberveglieri. And currently I'm working in Fondazione Bruno Kessler, and I'm also collaborate with Andrea Gallardo.
I know him very well.
And the main problem that we are facing with gas sensor, camera-resistant gas sensor, is the problem of selectivity. So my question is about selectivity, and then how you are dealing with that, with these electron nodes, if you are coupling with maybe some way to be able to be sure that which gas is in there, the humidity also. So just that, how you deal with that. Thank you.
Great question. It's difficult to give a good response to your question. Humidity, temperature, gas, and so on. Anyway, several groups in the last, I don't know, 20 years, maybe more, tried to obtain a selective sensor. Nobody was able to obtain. There's plenty of paper, nitrogen dioxide, I don't know, carbon dioxide, perfect sensor. It's not true. It's not true. That means are mainly sensitive at this gas, but there are other interferent gases give a response. That is why there is a successful to use an array of sensors, of course. And then the main activity nowadays is to use not so selective. Sometimes it's not important. It's important that are stable, because if there is a drift in the time, like in some organic compound, the path recognition method have to be updated. Updated means calibration. Do you imagine the calibration every week in the sensor is a disaster, no possibility to use that. The stability is very, very important of that. And the reproducibility, because in some cases, in the past, I remember in some electronic nodes, they broke one sensor, was broken. Have to change with the new one, but was different. The new one is better the old one. You have to start again to obtain the training of the electronic nodes. That is why the selectivity is a problem unsolved at the moment. To my idea, that's depending on the application, of course. If you have carbon monoxide, might be a very, very high concentration, is selective, and the interferent gas is very low. With some application could be enough, the nowadays possibility to obtain selective. But at the moment, is not solved problem. Absolutely not. Not only you, everything, in every laboratory, also in my lab, honestly speaking.
Okay, thank you very much.
Thanks. Niharika, you next, please.
Yeah. Thank you for the interesting talk. I'm just curious to know about the power consumption of electronic noses and what are the challenges in operating them.
It's an important question also, this one, because there are, I believe, two types of the electronic nose. One electronic nose applied at industrial level is not important power consumption because they use directly in the production line. Also, one of mine is in a big company, they would like to control the quality of the food online directly. No absolutely problem of the power consumption. But nowadays, there is also great interest to portable electronic nose. In that case, to battery operated electronic nose. That could be a big problem at the moment because the best sensor nowadays are made by metal oxide. They are working at 300, 400 degrees centigrade. Then I believe the minimum working power consumption of the sensor is about 0.2, 0.3 watt. That means we need a several watt because maybe an array of 6 or 7 sensors need 2 watt, 3 watt. That means that is a big problem with the batteries, of course. But we need that. And then there is a little work to reduce the working time. One of the methods that I used for the first time in my life was the first author used the light, UV light, in order to avoid to excite the sensor with the temperature. We use the LED, light emitting diode, UV. UV now is very low cost, very great on the market, large number on the market. In that case, the performance is not the same of the temperature, but reduce drastically the power consumption. I imagine in short time will be on the market electronic nodes, very low power consumption using light emitting diode UV. That is my idea.
Thank you.
Thanks. I see no other questions and we are, I would say, perfect on time. So Giorgio, thanks again for the very nice and interesting talk. And let's say my digital applause to you. And thanks again for having accepted our invitation. Thanks for being with us today. Thanks. Thanks, Stefano. Very nice.
Have you good work.
Thanks, Giorgio.
Bye.
Okay, so I think we can immediately move to our students' session. And so our first speaker is Nikhil Pillai. And his talk today will be regarding sensor selection and placement for track switch condition monitoring through validated structural digital twin models of train-track interactions. Nikhil, please, floor is yours. So I recommend you all, as I did yesterday with a private email, to stick to the 50 minutes, including the question and answer time. So I don't say any more words, so please, floor is yours.
Thank you very much, Dr. Mariani. Good morning, everyone. My name is Nikhil Pillai, and I'm a PhD candidate in railway systems engineering at the University of Birmingham. My PhD project looks at developing structural digital twin models for train track interactions for supporting the condition monitoring of railway track switches. So my talk today is going to be based on sensor selection and placement for the condition monitoring of track switches in particular. I aim at achieving this through the development of physics-based numerical simulation models of train track interactions, as I'll talk about now. So first of all, what is a digital twin? As the name implies, one definition of a digital twin could be a model or a virtual replica of a structural asset in operation. In our context, the digital twin simulation model can obtain information about the effect of the passage of trains over railway tracks by analyzing their interaction through the principles of structural physics and engineering. So this talk is going to focus more on the development of models to support sensor selection and placement. However, I will also briefly talk about how the models that I've developed can be deployed as digital twins. So like I said earlier, a digital twin is a virtual replica of an asset in operation. These models need to go beyond just being physical representations. Therefore, from an implementation point of view, I have recognized two ways of utilizing these models. So in the first approach, the simulation conditions in the model, which can be inputs from the field, can help predict rail damage directly. The second approach involves supporting condition monitoring by determining the strategic locations on the asset to fix or embed sensors. A condition monitoring system that processes the information obtained from smart infrastructures with these optimally or appropriately placed sensors can be implemented for effective detection and diagnosis of rail faults. So together, fault detection, fault diagnosis, and fault prediction will contribute to the delivery of the risk-informed predictive maintenance for railway tracks. So among track assets in the UK, switch and crossing, or SNC, are critical components that help trains change direction. They account for just 4% of the total UK track mileage, but they attribute to over 20% of the maintenance and renewal budgets for Network Rail, who is our infrastructure manager here in the UK. I have included an SNC schematic on the slide, as you can see on the right, to explain what SNCs look like. So the switch is essentially the beginning of the track diversion, where the train begins changing lines. So passing the crossing, which is on the right-hand side, leads to a complete change of the track for the railway wheel. From the analysis of previous data from Network Rail, we recognize that the main failure mechanisms for SNC rails are rolling contact fatigue, or RCF, plastic deformation, and rail wear. So let's look at these faults that arise from these failure mechanisms very quickly. So the failure mechanism of surface-initiated fatigue due to rolling contact can result in a number of surface-initiated faults. They manifest themselves in the form of cracks or indentations. So with regard to wear and plastic deformation, we can see faults that can be observed in the form of material removal and resettlement. So there are some very well-researched models to predict the failure mechanisms that we saw earlier. On this slide, you can see a few examples of the models that have been used traditionally to predict wear, RCF, and plastic deformation of the rails. So the inputs needed for these models, these damage prediction models, come from numerical simulations. So there are two main numerical simulation approaches that have been traditionally implemented for simulating train track interactions. They are multi-body simulations and finite element analysis. So multi-body simulations involve modeling the train and track components by using rigid elements. For example, the rails and the sleepers in my model were represented through masses. The connections to represent the track flexibility were modeled by using springs and dashboards. So the advantage of multi-body simulation is that it is very quick, and it also allows the consideration of detailed vehicle dynamics of trains, but they cannot consider material plasticity and perform subsurface analysis. On the other hand, in finite element, solid finite element models, complex geometry can be discretized into a number of finite elements and each element undergoes physical analysis. This approach is able to consider detailed material and mechanical behavior. However, it is also very computationally expensive. Therefore, we realized that the best approach would be to use a combined simulation approach that would allow us to capture the holistic effect of vehicle dynamics, as well as the subsurface material behavior that is needed to help us determine the placement of sensors. So I devised a 4-step methodology for modeling. In the first step, the results from a holistic train track MBS interaction model were used to obtain the locations that are susceptible to rail surface damage. Following that, I developed a detailed FE model of the local regions. The third step involved taking the boundary conditions of the model and validating them by achieving a good agreement for the track dynamics between the MBS, that is the first model, and the FE, that is the second model. So the first model has also been published already. So the results from that were validated against the field. So this is how we also validated the finite element model. Finally, I carried out rolling contact simulations and validations through comparing the results against the reference. So firstly, I predicted the locations that have a high risk of surface damage by using the whole life rail model that you can see on the left-hand side of the slide. So carrying this out, I obtained the signals of the wheel rail tangential forces from the MBS model and calculated the wear number, or T gamma. I then created a 3D model for a short length of track for these specific high risk locations for the more computationally expensive finite element analysis. For the accurate representation of the track in FE, I converted the track dynamic properties in MBS into appropriate material properties. So on the left-hand side of the slide, you can see the SNC FE model that I described earlier. I carried out analysis for the rail receptance first, which is the track deflection, across the frequency range of interest, and I compared it against the reference MBS model. As you can see in the top right-hand graph, a good agreement has been observed between the track dynamic behavior of the MBS and the FE models, so the FE model is representative. I then carried out wheel rail rolling contact analysis in FE. So the results for the vehicle movement were input from the MBS into the FE model, as the MBS model considers a more holistic effect and a more accurate effect of how the vehicle moves. As you can see in the graph on the bottom right, a good agreement was obtained for the contact forces that were output from the two models. There are certain discrepancies because of the level of detail considered in the vehicle dynamics, but it is an acceptable solution. So now that the FE model was developed and validated, I introduced a squat surface damage, which is very critical here in the UK, and it is observed very much on SNCs. I carried this out at a location where we predicted the highest risk of surface damage. I then ran rolling contact simulations or parametric studies for the rail profile with this damage. From the FE simulations, I obtained the results for the stresses as well as the true strains. The true strains that I obtained were then converted into engineering strains, which are essentially the strains that can be measured by strain measurement devices. So on this slide, you can see the results for the stresses on the railhead. So here, the overall amplitude for the stress is clearly higher for the model with the fault, that is the one on the right. On this slide, I have plotted the results from the rail cross section that experiences the highest impact force as the fault is introduced. That is one particular cross section. The results that you can see are for the change in vertical strains. On the left figure, the locations highlighted in yellow experiences a difference in strain of more than 5 microstrain. On the right-hand figure, I have adjusted the scale, and the results in yellow demonstrate the regions where a difference of more than 15 microstrains can be observed. So overall, the measurement of vertical strain can help detect the fault if the sensors are placed on the web of the rail on the track side, that is on the left-hand side of the track. Similarly, the results for the strains in the longitudinal direction have been shown on the left-hand figure of this slide. These are longitudinal strains. The difference in strains is the highest in the top and bottom portions of the rail. The top of the rail experiences the most compression, and the bottom experiences the most tension. The best location for installing the sensors for detecting the presence of the fault would hence be the rail foot, because you also get a good fatigue life for the sensor, as well as you're able to get good detection. Ideally, the placement of sensors in the lateral direction, as you can see here, will need the installation of sensors near the rail foot for the detection of the strains in the lateral direction. However, the difference in strains that's observed at this location is not good. Therefore, the placement of sensors in this orientation will need a low value for the sensor resolution. Now let's look at the distance up to which the fault can be detected effectively if vertical rail strains were to be measured. As you can see on the figure to the left, the strain gauge, if the strain gauge was to be placed on the rail bed, over every sleeper, the squat fault would be easily detected. So the length of one sleeper is more than half a meter, so it's 0.6 meters. So a sensor can be placed at over every sleeper to effectively detect the development of this squat fault. So this is if we consider the resolution of the strain sensor is at least 5 microstrain. The value for the strain gauge resolution can be adjusted in the plots to check the ability of a particular strain sensor to detect that present fault. In that way, we can also do time domain analysis and then determine whether a particular algorithm is able to detect the fault effectively through the virtual model. So if you want to implement such simulations for digital twins, we'll have to overcome a few challenges. Firstly, we need to obtain actual operational inputs from the field. This may include, for example, selection of an appropriate vehicle for simulation, weather conditions, train speeds, and track stiffness measurements. Secondly, the efficiency of FE models can be very poor for them to function as digital twins. Several approaches are being proposed to overcome this through reduced order modeling. The third challenge is ensuring model validity. This can be achieved by comparing results from sensors installed on the field against the results that are obtained from virtual sensors in the model. So these will be topics for future work. So I would like to end my presentation with 3 key messages. So firstly, models that are developed during the asset design phase can be implemented for taking important decisions in the maintenance phase. So the models that are developed for structural analysis when someone's designing something, those models can be used in the maintenance phase as well. Secondly, validated structural models of assets and their interaction with the external environment can help us locate places to monitor and also help us narrow down the sensor placement regions. And thirdly, live traffic data can be fed into digital twin models in the future for further optimization studies for sensor placement so that we have more data through the model and we can analyze that for sensor placement. Thank you very much for listening to my presentation. If you have any questions, please feel free to ask. And also, please feel free to contact me on my email address that I mentioned below for any further queries of our future collaboration. Thanks for listening to me. Thank you.
Okay, thanks, Nikhil. Thanks and applause for your presentation. Is there any questions? So we have kind of time for single question. Okay, if not, I have one. So you mentioned that the very hand, so the problem regarding traffic data. And so for instance, you showed that the amplitude of, in the change of the deformation can be in the order of, say, a few micro deformation.
Yeah.
So what would be, so if you imagine to use machine learning to try to classify whether you are in a good or bad condition. So how much would be the amplitude that you have to get rid of because of the data? So because of the working condition.
So we can detect the fault either in the frequency domain or we can also do time domain analysis. So if we are looking at the faults in the frequency domain, there are certain faults that give a response at certain frequencies. So we can classify the faults based on that. And then at those particular frequencies, we can look at the amplitude of the, for example, accelerations of the strains that we obtain from the sensor. And we have also noticed that it is in the vertical direction where the most change is observed. So, you know, it goes up to 200 microstrain as well for certain faults, but of course we have different faults. for the rails. So the one that I spoke about is most prominent, which is the squat fault on the surface of the rail. So for this particular fault, up to 15 microstrain, if the sensor is able to detect up to 15 microstrain, we will be able to effectively detect the squat fault. And then we can also look at the frequency at which it is acting. So we can get the appropriate results for that from there. And along with this, we can have various other sensors that can be installed on other parts of the rail. And by having a sensor array and by looking at all the information together, we will be able to better determine whether a fault has occurred or not. Otherwise, we can also have anomalies that, it's a very dynamic environment, and you have lots of different kinds of trains passing. So we need some sort of sensor fusion to effectively determine the presence of a fault. So I hope that answers your question.
Yes, perfect. Yes, thanks again for the very nice presentation. Again, our applause.
Thank you very much.
Okay, thanks, Nikhil. I think it's now time to move to our next speaker, who is Xinyi Wang. Beg your pardon in case my pronunciation was not good. Talk will be regarding conceptual designs of the rotation mechanism with anti-phase energy harvester.
Today, I will recommend my topic of conceptual designs of the rotation mechanism with anti-phase energy harvester. Xinyi Wang, Wen-Song-Hu, Jing Xianxu, and Chang Ping-Sen finished this project together. And my presentation will be divided into 6 parts, include introduction, type of vibration energy harvesting, rotation anti-phase energy harvester, experiment setup and its results. Finally, I will give a conclusion. Let's start. The demand in wireless sensor has increased in the recent years. According to the IDTechX latest report in energy harvesting, much of the data are targeting in improving people's life, especially in the smart cities. And the data is connected wirelessly through wireless sensor nodes. Data Bridge market research shows the vibration energy harvesting market expected to be increased until 2027 with a demand growth of 9.1%. And in previous, we use battery to provide power to the wireless sensors and connect it to the grid. But there exist some problems. For battery, it needs to be replaced after a certain years, and how to deal with battery disposal is a big issue. Also, connecting it to the grid will bring some problems, such as the cost of installation if large amount of sensors are involved. So we don't use a battery. One of the possible solutions to supply energy to the wireless sensor is energy harvesting. It includes wind energy, solar energy, kinetic energy, and vibration energy. Vibration energy is harvested from the vibration motion, and it is applied in our project. For the vibration energy harvester, there exist 4 main types of vibration energy harvesting, include piezoelectric, electromagnetic, electrostatic, and triboelectric. Among these 4 types, electromagnetic require low voltage and can produce the highest power. So it is the best option, and we use it as a working principle in our prototype. In the previous research, anti-phase has been proved can provide double voltage, and the power will be larger at the same volume. Also, using the mechanical design, slow rotational of any mechanical device can convert it in an unidirectional up-down motion. So in this program, we propose a conceptual rotational energy harvesting designs for slow rotation, and we hope to investigate the amplitude amplification through the springs and identify the best arrangement of springs location. The working principle of the prototype is to utilize the rotation to generate the vibration through the repulsive magnetic force. Generally, the base vibration is produced from the repulsive magnetic force, which is present in the rotor. There are 3 prominent magnets on the rotor, and another same dimension of the magnet attached to the upholder to produce a vertical movement. The antiphase energy harvester also connected to the linear guide rail. There are 2 springs in the system, base and antiphase springs. The motor is used to rotate the rotation disk that mimics the behavior of the real system, which connected to the rotor through the same pulley dimensions. This is the experiment setup. In the experiment, the different spring positions on the prototype were studied to identify the best arrangement that harvests the maximum power. For harvester, the maximum power is the 4 configuration of the spring position were identified where the base and antiphase springs were installed. And 4 different spring positions are D1 top bottom spring, D2 top spring, D3 bottom spring, and D4 no spring. The top and the bottom springs are referred to the antiphase and base spring, respectively. The motor was operated at the speed from 200 RPM to 4000 RPM with a gear ratio of 5. And this is our experimental video. You can see how it works. This figure shows the time response curves of absolute base amplitude and angle for complete revolutions for D1, the top and bottom spring at 600 RPM. The blue line shows the base amplitude and the red line shows the angle. You can see there are 3 peaks in one revolution. This is because there is 3 permanent magnets in the rotation disk. When the magnet in rotation disk meets the magnet in top part, and when these 2 magnets in a line, it will cause the biggest repulsive magnetic force and lead to the biggest amplitude. Another small 3 peaks from the empty gap between the magnets is because at that time there is a gap in the rotation disk, and another side is a magnet in the top part. And at that time, the repulsive magnetic force is very small. This is the experiment results, and the figure shows the relationship between the amplitude and the frequency. And this is the amplitude hidden in the rotation disk and the top part. You can see in the figure, the D2 and the D4 has the lowest amplitude and close to the 0, and the D1 top and the bottom spring and the D3 bottom spring has the obviously peaks. The performance of bottom spring configuration is better than both spring configurations at a low frequency range, 0 to 30 Hz. And for the bottom spring, it has the maximum amplitude when the frequency is 12.5 and the maximum amplitude is 6.43. This is also the figure shows the relationship between the amplitude and the frequency happens in the antiphase. Similarly, the D2 and the D4 has very low amplitude, and the D1 and the D3 have obvious peak. For the D1, it has the maximum amplitude happen in the when the frequency is h.5 and the maximum amplitude is h.70 millimeter. And for the D3, the bottom spring design, it has the maximum amplitude as 6.5 H when the frequency is 12.5. The resonance performance of D1 is generally better than other designs when the frequency is lower than 10 Hz and larger than 21.5 Hz. And D3 takes advantage when the frequency is between 10 and 21.5. This is a figure shows the voltage produced by the antiphase and its frequency. The peak here means there are more energy created and the system is more effective. You can see in this figure, the maximum voltage is occur in D3 bottom spring design. And the average voltage of D1 is generally lower than D3 for almost all the frequency range between 0 and 40 Hz, except for 10 Hz and 27.5 Hz, where true voltage peak occurs. And the maximum voltage created in our environment is 1.78. In conclusion, the experiment shows the bottom spring has a significant effect on the amplitude and voltage amplification, but the top spring might contribute inversely and impact the performance to some extent. However, the combination of top and bottom springs can produce a better performance at a certain frequency range. The proposed concept designs are useful for the wireless sensor nodes to provide continuously power for the sensors to operate. In the future, we plan to change the material of rotation disk to improve the magnetic flux and further increase the voltage. This is the reference. Thank you. Do you have any question?
Thanks. Xinyi, for your presentation, our applause. And we have time for one question.
Yeah.
See no questions, so I have one. So you, in the pictures you showed in the very last slides. Regarding the design D1, there were 3-4 peaks in your graph, right? Regarding the design D1, there are at least 3 peaks.
Yeah.
And that means that you are exciting this frequency range 3-4 vibration modes. So if you return back to the geometry or even to the movie, so what type of modes are those excited in this range, and why don't you have, for instance, in the other geometries?
There's 3 peaks. I think the reason why it is created is very complex, but it is from the experiment, and I got such result. And because although the maximum amplitude is happening in the frequency close to the 30, but more frequency means more voltage is needed. And our aim is to use the less voltage to create the big amplitude. Also, it means a big power because it is the amplitude in this part. Means if amplitude here is big, also will create the antiphase to have a bigger cut-off motion and to create a better voltage. And so we want to use the voltage less to create the antiphase generation voltage more. So I think although the 30 frequency here can get the good amplitude, but it asks too many voltage input, so we don't use it.
Okay. Okay, thanks for your answer. So again, our applause. And I think it's now time to move to our next speaker, who is Elisabetta Bodo. And she will talk about microfluidic devices with selectable optical path lengths for quality control of alcoholic solutions, exploring NIR spectroscopy properties of water and ethanol. Elisabetta, please, the floor is yours.
Okay, thank you, Professor Mariani, for the introduction. So good morning, I'm Elisabetta Bodo, and I would like to present the research activity carried out with my colleague Valentina Bello at the Laboratory of Electro-Optics of the Department of Electrical, Computer and Biomedical Engineering on the University of Pavia. Our work was about the development of microfluidic devices with selectable optical path length for quality control of alcoholic solutions. We developed a micro-optofluidic platform for the identification of fluids exploiting their absorption properties and features in the near-infrared wavelength region. We used the rectangular glass microcapillaries provided with integrated reflectors. Capillaries are low-cost devices commercially available in several formats that are composed by borosilicated glass. That is a transparent, biocompatible material. Thus, this platform are suitable for the analysis of biological fluids and for biochemical and biomedical application. Thanks to their micrometric size, capillaries allow the analysis of ultra-low volumes of fluids in a contactless, remote and non-invasive optical investigation. Moreover, thanks to the flat surface of the rectangular section capillaries, the light scattering is reduced with respect to the round section capillaries. In a previous work presented last year for the 7 Electronic Conference on Sensors and Application, we exploited microcapillaries that was laid onto a bulk mirror in order to test the absorption features of pure fluid sample, for example, ethanol, water, isopropanol, ethylene glycol, in the near-infrared wavelength region from 1 micrometers to 1.7 micrometers. This is the setup that we used. Light from a tungsten lamp was coupled into a multi-mode fiber optic patch cable and shown on the device under test using a pigtailed lens. After crossing the capillary only twice, since light bounces on the bulk mirror only one time, the output light is collected by another pigtailed lens that is located at the same side of the input lens, and it is finally directed toward the monochromatic input of the optical spectrum analyzer that is connected to a leptor for data elaboration and acquisition. The fluid to test is injected into the channel using a syringe, and after the measurement, the fluid is ejected using an empty syringe filled with air. In this case, light crosses the capillary only twice, and the results were promising, but in this case, the structure was difficult to handle and it is not suitable for implementing a sensing platform. For all these reasons, in this work, we presented a microcapillary provided with integrated external reflector. Using this technology, we have developed a smart and compact micro devices. The aluminum layers on the top and bottom of the capillary are deposited by sputtering. That is a simple and low-cost technology. And in this way, light can cross the capillary multiple times. Indeed, by properly selecting the input position of the beam, the light can create a zigzag effect into the capillary. And this platform is suitable for sensing purpose, and thanks to the multiple bounce configuration, the sensitivity is enhanced. We expand our research not only for pure substances, but also for mixtures. And at the right, we can see a picture that is a photograph of the capillary in comparison with a coin in order to emphasize the small dimension of the device. We develop a sophisticated theoretical model implemented in mental environment in order to perform simulation to obtain analytical results that could be compared with the experimental one. The model takes into account the dimension and the features of the capillary that can be viewed as an optical structure composed by different layers. The channel in which the liquid flows that is located between two layers of glass, and the metallization that acts as reflectors with a reflection coefficient of 0.29, and all the structures is immersed in air. The propagation of the light beam can be described using the geometrical optical residency approximation. We suppose that the incident light is a plane wave, the interfaces between media is flat, and media are homogeneous and isotropic. Figure shows the longitudinal section on the rectangular capillary in case of free bounces into the structure, which takes into account the refractive index of each surface. In particular, for the fluid that is filled in the channel, we consider not only the real part N, but also the imaginary part of the refractive index in order to take into account the absorption features. We calculate the optical path using the Snell's law, and the transmission coefficient for the power at each interface was calculated using the Fresnel's formula. And in order to take into account the absorption, we consider the Lambert-Beer law. In terms of transmittance, it is related using an exponential relation with the optical path and alpha, that is the absorption coefficient, related with chi, that is the imaginary part of the refractive index, and the wavelength. The behavior of the absorbance as a function of the wavelength is a characteristic fingerprint of each molecule, and the value of the refractive index comes from literatures. We developed the model that works for both single bounce configuration and multiple bounce configuration, and it works also for pure substances such as mixtures. In case of mixtures, we use the additivity of absorbance to calculate the absorbance of the fluids and of the mixtures. The absorbance is the sum of the absorbance of each fluid contained in the mixtures multiplied for the corresponding fractional volume concentration. And we use the additivity also to calculate the real part of the refractive index of the mixtures. As we can see in the figure at the right, we compare the performances of the configuration with one bounce and multiple bounces. We perform a simulation in case of 7 bounces into the capillary. And we can see that the multiple bounce configuration allows to increase a lot sensitivity. Moreover, it allows to observe more detail of the transmitted power spectrum. For example, I reported a simulation that we did for isopropanol, ethylene glycol, and the mixture of ethylene glycol and isopropanol at different volume concentration. And we can see the peak that is characteristic of this solution at 1.185 micrometers. To perform the spectral analysis, we carried out experiments by filling the channel with mixture of ethylene glycol and isopropanol in different volume concentration. For increasing ethylene glycol content, the transmitted power between 1.4 and 1.6 micrometers decreases, since ethylene glycol does act with two absorption band around this wavelength, as we have seen in the previous slide when I performed simulations. And we was able to distinguish all the mixtures. Part of our work was focused on the implementation of the optical sensor for specific sensing of ethylene glycol. It is well known that when implementing an optical sensor based on amplitude detection, it is important to select the power at 2 different wavelengths in order to eliminate spurious variation that are not induced by the quantity under measurement. For this reason, we selected 1.46 micrometers, since it corresponds on an absorption peak of ethylene glycol, and 1.35 micrometers because it is a wavelength where both ethylene glycol and isopropanol are only weakly absorbing. By calculating the logarithmic value to base 10 of the ratio of the power at these 2 selective wavelengths, we retrieved the responsivity parameter that is specific for ethylene glycol content. And we calculated this parameter that we have identified for all tested solution and all ethylene glycol content. In this way, we retrieved the experimental calibration curve. plotted in the figure at the left side of the slide. And by linearly fitting the data, we retrieve an equation that is the equation of the calibration curve, and the slope of this curve represents the sensitivity. Finally, we retrieve the measured ethylene glycol content from the equation, and we plotted the measured ethylene glycol content against the theoretical ethylene glycol content, as I show in the figure at the right side. And we can see that the data are almost superimposed to the bisector, thus measurement agree with theory. To conclude, in this work, we have reported a smart and compact microfluidic devices based on rectangular section glass microcapillary in order to detect fluids, pure substance in such mixtures based on their absorption properties. The microcapillaries is provided with integrated reflectors that are deposited by sputtering, and the light in this way that is emitted by a tungsten lamp crosses the channel multiple times. We was able to distinguish mixture of isopropanol and ethylene glycol at different volume concentration, and finally we have identified the two wavelength ratio error as sensor responsivity parameter, and the specificity for ethylene glycol content has been verified. We wish to thank Professor Sabina Mello for her fruitful suggestion, and thank you for your kind attention.
Thank you, Elisabetta. Say digital applause for your presentation. We have time for questions. So Elia, I see your raised hand. Okay, so yeah, please.
Good morning. Very interesting talk. Thank you. I have honestly two questions. The first one is about the number of bounds that you made. The question is the higher the number of bounds, so the higher will be the sensitivity?
Okay.
Or, I mean, it's a linear, or it's after, I don't know, 10 bounds, then the selectivity is going to be
okay. Common. Regarding the number of bounces, thanks for your questions. We perform simulation to obtain the number of bounces, and it is calculated using the formula in this slide. So we consider the length of the metallization on the upper side of the capillary in accordance with the experiment. We used capillary with 5 millimeters and 4 millimeters. With 5 millimeters, we obtain 7 bounces for the solution tested, and so for both isopropanol, ethylene glycol, and all the mixture of ethylene glycol and isopropanol, we obtained the same number of bounces that was equal to 7. Whereas for a metallization of 4 millimeters, here I didn't present the results. We obtain 5 bounces into the structure, and the number of bounces is an important parameter because the sensitivity of this system depends a lot of the number of bounces. So by incrementing the number of bounces, the sensitivity is really enhanced. And it is possible to view these features on the slope of the calibration curve.
Okay, I have another one, if I may.
Okay.
I don't
Yes,
know if
yes, if it is quick, yes.
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 With this device, are you able to extract the refractive index of an unknown liquid, or you have to know before the liquid almost the concentration of liquid that you insert?
No, it is possible to obtain the refractive index of the solution we tested.
Okay. Okay. Thank you.
Okay.
If you have a question. Okay.
Okay. Thanks, Elisabetta, and thanks, Elia, even for the very interesting questions. Thanks. Okay, so again, applause for your presentation. And I say it is now time to move to our next speaker, who is Vishal Allada. And the presentation is related to computer vision technique for blind identification of modal frequency of structures from video measurements. So Vishal, please, floor is yours.
Hi everyone, and thanks for the introduction. As mentioned, my name is Vishal Allada, and the topic for the presentation is computer vision technique for blind identification of modal frequency of structures from video measurements. And Dr. T. Jyoti Sarvanan is the co-author for the work, and also he's my guide for the project. So the contents and the organization of the presentation are as follows. The first I'll discuss about the objective, followed by the methodology, then validation both on numerical and experimental models, and then implementation on real life structures, and finally concluding the results. So the main objective of this study is to develop a hybrid computer vision based technique to extract the modal parameters of a vibrating structure from its videos. So using the computer vision techniques and the analytical techniques like analytical mode decomposition and a statistical technique like principal component analysis, the technique has been made, like methodology has been proposed to extract the modal parameters. So to exactly know, to know about the methodology. So first we'll move on to the methodology. Like it's a brief explanation and a schematic diagram for the methodology. So as we can see, the methodology is like mainly divided into two parts. So the first part is majorly concentrating on the computer vision techniques to obtain the phase of the each pixel of the video frames. So actually why we are extracting the phase? Actually the phase of a video contains the motion data of the structure. So to extract that motion data, we are using a technique called complex steerable pyramids, and we are extracting the motion data. So this motion data is later used in the second phase, that is to extract the modal parameters of the structure by using the different statistical and analytical techniques. So in the further section of the slides, I'll briefly explain about these methods. So the PCA and the PCA, also known as principal component analysis, and the AMD plus RDT technique is being has been demonstrated in the numerical method, but the complex steerable pyramid, which is also being used, is not shown in the numerical validation. So to have a brief idea what is the use of this complex steerable pyramids in the current work. So I'm going to as we can see, this is the schematic of the complex steerable pyramid, and as we can see, it is actually divided into two parts. The left part is like the construction of the pyramid, and the right part is the destruction of the pyramid. To be frank, the construction of the pyramid means it refers to the decomposition of a given image into various levels and orientations, and the destruction of the pyramid refers to reconstructing the image with the decomposed levels and the orientation. So in the present research, we are mainly concentrated and interested in the decomposition of the image, that is construction of the pyramid. So as we can see, if you input an image, so the complex steerable pyramid initially divides the image into two parts, high frequency part and a low frequency part. So the low frequency part is again sequentially divided into, means recursively, it is divided into multiple levels with different orientations. And in this work, we are mainly concentrated on the first orientation, which contains the majority of the motion data. So this is the ideology of what is a complex steerable pyramid and why we are using this here. And now we move on to the methodology where I'm going to explain how exactly the AMD, PCA and the RDT are being used. So for the validation purposes, I have used a 10 DOF system, spring mass model. So the 10 DOF spring mass model contains all equal masses except for the last and first mass, and the spring constants are all equal. For the computational purpose, the damping matrix for the entire system has been taken proportional to the mass matrix. So after suppose in this model, theoretically there are 10 modes are possible, but to demonstrate how PCA and AMD works, we again a new 10 channel response has been generated by using the theoretical theoretical modes which are generated by Newmark beta algorithm. After getting the theoretical modes, the first 4 dominant modes are used to create a new 10 channel output. So this will work like a high motion matrix data with less number of modes which are representing the motion. So to separate this, we can use a statistical famous statistical technique known as principal component analysis. Basically, principal component analysis reduces this high dimensional data to a low dimension data without losing its without losing the majority of the information. So in this method, the PCA is used for the dimension detection of the high motion matrix which is constructed. In this case, the high dimension is like the 10-channel output, and the 4 modes are like the dominant and they are the major components. So the PCA has to extract the 4 components, and then the principal from those principal components, the analytical mode decomposition, which is a Hilbert-based analytical time series based decomposition, which can be used for mode separations. So the AMD is being used has been used for getting like the principal components which have been extracted. So after like the AMD has been like the modes have been separated, so then to obtain the model parameters, the random decrement technique has been applied on the separated modes, and from the random decrement signature, logarithmic decrement technique is used to obtain the model parameters, both the damping ratio and model frequency in this present case. So as if you see move to the results part, there are like 4 principal components have been identified, and each principal component is a mixture of all the 4 modes with different energy levels. And as you can see, the principal components, like these are the principal coordinates on the left side, and the right side represents its power spectral density. So the power can be related directly to the like the power of the dominance of a mode in that particular signal in that principal component. As we can see, like all 4 components can't be extracted like from a single principal component. All 4 equally contribute. So they all 4 are like simultaneously fed as input to the analytical mode decomposition technique, which is a Hilbert-based transform. So after like using the technique, we generate the 4 modes. Like the 4 modes have been obtained. As you can see, they are like the frequencies are also like identified, and the damping ratios are estimated by using the random decrement technique, which is applied to those model coordinates which are extracted and represented in figure 5. So after extracting the random decrement signature, the damping ratios and the frequencies have been estimated, and the comparison between the theoretical like the calculated values and the estimated values have been presented in the table 1. As you can see, like the difference, like the error in the identification of the frequency is less than 1%, and the identification in the damping ratio is less than 2%, like which can be considered as a good agreement like to consider the method. So this is a numerical method which actually validates the PCA plus AMD. So the robustness of PCA plus AMD to validate the like the CSP technique, the complex steerable pyramids. We have used a laboratory video, like a multi-degree of freedom system, which have been obtained from the internet source. So to have like now to put it in a like a whole on a whole, as we can see, this figure 6 is the implementation algorithm, which is like there's a brief explanation like what is happening in the method. So initially a frame is taken and it is decomposed into its corresponding amplitude part and phase part. So the phase part contains the motion data. So actually the motion data comes with a noise and like a temporal mean associates, which deviates the actual value, like the display motion data. So to remove that, we temporarily filter the phase part, and then after filtering it, the motion matrix is constructed by using all pixels data. So actually we use all the pixels. So if you can consider the image, in this case, the image we have used is like 240 cross 180. So if we like that is a huge huge number of pixels. So which can't be practically, it's impossible to process the entire data. So to reduce the dimension of this data without losing the motion data, we use the principal component analysis to extract the principal components. So after extracting the principal components, as mentioned, like in the numerical method, the rest of the method is same. Like we input it to the AMD mode model, and then the analytical mode decomposition gives us the values like the separated modes, and then RDT is applied on the separated modes. to obtain the logarithmic decrement technique. And from there, we can estimate the damping ratio and modal frequency. So this is like an entire methodology, like explain methodology, a brief way. So we have performed the experiment on like the experiment, like it is a experimental video which has been taken from internet source. And the experiment was performed by Professor Wang in 2008. So actually the test is about to show the resonance of an MDOF system to the vibration table, as we can see in figure 7. So this video was uploaded in YouTube and we have used it for the current research purpose. So from this video, like we are able to extract the 2 modal frequencies successfully, and those 2 modal frequencies have been like has been displayed in the results table. Like there is a third mode also, but we couldn't identify the third mode because the mode has been like the modal frequency for the third mode is above 15 Hertz. So that's a limitation. Actually, the frame rate also matters, like how much, like how large the frequency can be extracted. So as the frame rate is 30, according to the Nyquist, so we can extract till 15 Hertz as the sampling is 30 Hertz. So we can decide like find till 15 Hertz. So like the third frequency is above 15, so we couldn't find it. And after extracting the 2 modal frequencies, like we have compared with the values which are given in the video. So, and the values are like again in good agreement, as the error is again less than 2%. So to still show the validity, as it is an laboratory controlled experiment, so to still show the validity of the method on a real on a real life scenario, we have implemented the entire method on two actual like real life cases. One is London Millennium Bridge and Tacoma Narrows Bridge. So first, the London Millennium Bridge. So as you know, like London Millennium Bridge is opened on June 10, 2000 initially. So on the same day, like after the pedestrians like started moving on the bridge, like a lateral swaying of the bridge has been observed. Actually, the lateral swaying is due to the wind plus the gait of the pedestrians. Like it matches the resonant frequency of the structure. So they can say actually, and at the time, a lateral sway has been observed. So this video is also uploaded in YouTube. So from this video, like we extracted the modal parameters. Means to be like precise, we extracted the modal frequencies and compared with the existing literatures. So as we can see, like initially we have the region of like the bridge is actually swaying, and there will be all motions at the part of the girders and everywhere. So we cropped the region, like the entire video, to the cable region where we can see only the dominant like the motion in one direction. So as we can, like this is the cropped region which is represented in figure 10, and then like the complex steerable pyramid is used to like differentiate like into 2 parts, phase part and amplitude part. So again, the phase part is used, and after following the entire method, like the results have been obtained and they have been compared with the references, like with the Pavia et al. Like it's the key findings of the London Millennium Bridge, which is published in 2002. So according to that literature, we have compared our frequency values, and they are also in good agreement. Actually, they are 99% accurate in identifying the modal frequency. We couldn't identify the damping ratio because of the less length of the video which is available online. If we would have a little bit larger video, actually the length here we used is for 8 seconds and the frame rate is 30 Hertz. So the data is not sufficient to use random decrement signature and to identify the like damping ratios. So if we could have a larger, like due to the constraint, here we couldn't identify the damping parameters. So next,
Vishal, please move to the conclusion. Time is over.
Yes. Okay, sir. Thank you. And we have similarly implemented in Tacoma Narrows Bridge, and we can see the results again are in good agreement. So in the conclusion, we can conclude that the method has been proved to be a potential method for doing the operational model analysis. As we can see, the results have been in good agreement. and the research is being continued to use it in the structural health monitoring for identification of the damages. And these are the references used in the video, and thank you.
Thanks for the very interesting presentation. Applause. And sorry, but we are running out of time, so we have to switch immediately to the next speaker, who is Andrea Altomonte, and was going to make his presentation titled "A New Three-Phase Smart Meter for Cloud Connection, Network Architecture and Performances." Andrea, please, the floor is yours.
Good morning all, and thanks for this opportunity. Today I will introduce you to our work regarding a new three-phase smart meter. I will start by introducing you to the smart grid. We will get through its technology and of course the meter network, which is the most innovative part of our research. At the end, I will show you the results of our testing and library, which validate the correct functionality of the smart grid. Historically, the main scope of the energy metering is billing. Since 1889, the only innovation applied to these devices has been remote metering. Actually, in all of Europe, the traditional smart metering grid is made of two components. The smart meter 2.0 measures power and energy in a preset time and sends this data to the data concentrator. The data concentrator, which is the key element of this topology, has the role of collecting and managing the data transmitted by the smart meters. Unfortunately, this kind of traditional smart grid presents two major gaps. The topology itself is unidirectional. The second one is related to the protocol used for data transmission. The protocol used is the power line communication, PLC, that transmits the data through the electric grid. This protocol presents a lot of drawbacks. The major one is related to an unreliable communication quality, and the second one is cost related. To overcome these limits, it's necessary to use a new topology of the smart grid. The current state of art from the scientific literature is Internet of Energy, which is a new concept of smart grid. The topology, in fact, is bidirectional. In this way, it's possible the presence of a prosumer within the grid. The prosumers represent all the people that produce and consume energy inside the smart grid. For example, all the households that have the photovoltaic system. The adoption of this new smart grid is strictly related to the use of a new type of smart meter, also known as a cloud meter. The purpose of our project was to design and implement this new technology. In the slide, we can see the block diagram of the designer hardware architecture. It is made of 4 macro blocks that ensure all the functionality of the proposed smart meter. The elaboration blocks allows the design choice between more microcontrollers based on the feature that you want to achieve. For the test of library, we choose the STM32 microcontroller produced by ST Microelectronics. It's a high-performance microcontroller that mounts an ARM SoC Cortex M7. The communication block serves the communication feature to the cloud and offers a different choice of communication. A special mention goes to the narrowband IoT protocol. The measurement block consists of 2 shields produced by ST Microelectronics, specifically for the smart metering application. They measure all the information from the electric grid. Finally, all the blocks are powered by the power supply block that has the role of converting the alternate voltage of the electric grid to a 5-volt DC voltage. Now, the main metrological characteristics of the used measuring traducer are reported. They have an input of nominal voltage that goes from 0 to 300 volt and the possibility to read up to 100 ampere. Furthermore, the presence of 4 independent sigma delta DC ensures reliable conversion. As I said before, our key technology for the proposed smart meter is the designed meter network infrastructures that abandons the old-fashioned PLC and embraces one of the most advanced IT protocols, such as the MQTT. The network involves a cloud meter and involves a cloud server that is the hub of our designed meter network. The network server is made of an MQTT broker and a database where all the data are stored. The smart meter communicates the data to the cloud server, which the end user can access all the required data through a web app. Before introducing the prototype of our smart meter and the test field delivery, it was necessary to test the network infrastructure as well the cloud server implemented. The cloud server was installed in a virtual private server with the specification shown in the table. The test consisted of a simulation of a smart grid as big as the entire city of Lipari. In fact, the number of users was set to 7,000. In this slide are reported the results of the stress test conducted. From the table, we can spot there was an error of 0% regarding sending and receiving meteorological data from the cloud server. Meanwhile, from the chart, we can remark an average usage of the hardware utilization under 10%. From these results, we can notice that the number of users can easily scale. Now we can go through the firmware programmed on our 3 smart meters. It consists of 4 modules. Starting from the bottom, we can see the 2 layers with the lowest level of abstraction, which are related to the drivers devoted to correct functioning of the microcontroller and the various metrological devices. The next 2 layers are the one related to the application layer. The application layer itself consists of 4 different tasks that run on a real-time operating system kernel. For the purpose, the proposed smart meter was used the FreeRTOS. So the firmware architecture consists of 4 tasks that ensure the overall functionality of the smart meter. The firmware routine starts with the generic task that initializes the hardware and the network. Notice also the presence of a diagnosis fault subroutine that could be called from other tasks in case of anomalies. The metrological task measures all the data from the electric grid periodically and store the data in an encrypted and pre-allocated memory area of the microcontroller. After that, the parser task retrieves this data and parses the data in a string using the protobuffer protocol made by Google. These steps plays a vital role to ensure a better and simplified security process and facilitate communication. In the end, the MQTT task first connects to the cloud server and then sends the meteorological data. In this slide, we can see the prototype of our proposed 3-phase smart meter. I conclude now with the presentation of the test field in Lipari. The test was conducted to validate the right operation of the prototype and the meter network realized. The test was carried out by installing a tiny smart grid composed of 3 different smart meters. The 3 smart meters diverge from the effective number of the phase. We installed a single-phase meter in a home environment and 2 3-phase meters were installed in an industrial environment. In the end, was designed and realized a web app or rather a dashboard to view the meteorological data in real time. Now, through a series of screenshots, I will describe the main feature of the dashboard. The main page is the overview, where it's possible to see the major data from all the smart meters, such as the chart of the active power, energy or reactive and ambient power. In addition, the statistics page gives more information about the stats of energy utilized and power consumed. Moreover, the details page shows the charts of the active, reactive, and ambient power for each phase of each smart meter. To sum up with, our work seeks all the new aspects of the modern smart grid. In particular, the proposed cloud meter matches all the most advanced requirements in terms of security and communication, since it uses the MQTT protocol and could be equipped with 5G communication. In the end, I want to stress the benefits that arise from the adoption of our technology in a modern smart grid. Our smart meter guarantees a reliable connection between the provider and the consumer and the real-time data communication. These 2 aspects lead to the provider to a better real-time modelization of the redistribution of the energy within the electric grid. This aspect results in a lower energy consumption and then in a lower CO2 emission. Thank you for your attention.
Thanks for the very nice and interesting presentation, as usual, Digital Plus. And so is there any questions online? If not, so as usual, out of curiosity, since it is a bit far away from my expertise, so you said that basically you showed that the workload on the server was not so big for the entire city. So you mentioned that it can be scalable. So
Yes.
is there, and I would say that the workstation, let's say, the computer you use was not so so specific features. So that means that the control of the network is rather easy using what you're proposing, right?
Yes, basically this test was conducted to highlight the fact that this network is a really reliable network and ensure all the functionality of the smart meter and also the real data transmission of the meteorological data from the electric grid. The test in itself, in fact, was carried out by emulating the grid of the city of Lipari, which consists of the number of users set to 7,000 of clients, we can see.
Yes, yes, I saw. And so do you think that, so in order to do this kind of real-time analysis of the load on the grid, so is the, let me say, topology of the network, so the kind of the plan of the city affecting much the solution, or is it really totally independent of?
No, it's totally independent from the stress test and the network, the smart meter network infrastructure.
Okay, that means that's very good. So because independently of the number of users and independently of the say the plan and size of your city, so basically you can have a quite easy analysis in real time of the stress in case of a stress test. No, that's very good. Okay, very good. Thanks. Thanks.
Thank you.
Is there any other questions? Okay, if not, Andrea, thanks again for the very nice presentation. We can move then to our next speaker, who is Elia Scattolo, right? So,
yeah, right.
The title of his presentation is Optimization of Focus Ion Beam Patterning Parameters for Direct Integration of Plasmonic Nanostructures on Silicon Photodiode. Please, Elia, floor is yours.
Thank you. So good morning to everyone. My name is Elia Scattolo. I'm an Italian PhD student, and currently I'm working with Fondazione Bruno Kessler, that is a research institute of the north of Italy, and in collaboration also with the University of Bodo, still in the north. And today I want to introduce you to my research topic that also aims to the optimization of the focus ion beam patterning parameters to direct integration of metallic plasmonic nanostructure on silicon photodiode. Just a brief overview on the facilities and my research group expertise. So my research group is focused on sensor in general, so micro and nano sensors. So we are used to work in clean rooms that are laboratories with controlled environments, and we are focused mainly on the light detectors, so silicon photodiodes. And among all these light detector, the more challenging is the silicon single photon avalanche diode, ECSA-8, because it's a type of sensor that is able to detect and then transduce single photon into a measurable current with a very great time resolution. So the possibility to achieve single photo counting in the near infrared is of interesting of many applications. Just thinking about automotive driving, to fight building without digging, or also for LiDAR systems, so light detection and ranging. That usually works in this way. We have a source that usually is a laser that emits photons. The photon interact with the objects and then collected by single photon avalanche diodes. This type of sensor is based on silicon technology, and because of the low cost of the well-established processing technique, and also for the properties of silicon. For example, it is thermally stable and for its high hardness. The main concerning to use silicon in near infrared region is that silicon has a very low absorption coefficient in the near infrared. And therefore, this issue hindered the quantum efficiency, so the efficiency of the device. And in this, in here, my research topic takes place. So during my PhD, I proposed to couple plasmonic nanograting with on top directly on silicon photodetector to be able to confine the light and therefore the photon inside the detector and increase therefore the absorption. The idea behind is that thanks to the plasmonic resonance, we are able to confine photon and therefore to increase the time that the photon is spent inside the device. In this way, even though the absorption coefficient is very low, we are able to increase the absorption of the photodetector. Among all the plasmonic structure that have been studied up to now, I decided to work with plasmonic metallic nanograting, both one-dimensional and two-dimensional, because of its easy integration and easy plasmonic properties tunability. Here in the slide, I show a cross-section of the structure that I proposed. That is, starting from the top, we have the plasmonic metal nanograting made of silver with a certain periodicity that also called pitch, and with a very small slit, that is the empty space between one dot to another. Then going down, we have the electron material, that in my case is silicon nitride, that is necessary to satisfy the condition to excitate the plasma resonance. And then we have the detector. Before starting the production, I ran some simulation, precisely some finite difference time domain simulation in numerical, to optimize the geometrical parameter of the structure, the plasmonic structure. Here in the slide, I report a heat map of the absorption of the integrated device, so this one, normalized to the absorption of a reference diode, that is a diode without nothing on top. All the simulation have been run at 950 nanometers, so in the near infrared, and they are a function of the periodicity along the epsilon axis and on the dot A, so the metal thickness on the x-axis. As is clear from the heat map, 4 different configurations are helpful for my purpose, so that I divided in the blue and the red one. The blue one presents 2 different periodicities, so 2 different optimal pitches that are 530 nanometer and 260 nanometer, but with a very high metal thickness of around 300 nanometer. The red one configuration presents the same pitches value, so 530 nanometer and 260 nanometer, but with a lower metal thickness. For that reason, analyze this type of structure from a fabrication point of view, it came out that because of the too high aspect ratio of the slit that must be produced, the configuration, the blue configuration, so the configuration with the high metal thickness cannot be fabricated, or at least the fabrication is very challenging, because this very high aspect ratio of the slit gonna lead to a very low lateral definition of the structure, and because of the large area of the detector, also to a long pattern time. On the other hand, the red configuration can be fabricated, and also the structure that we're gonna be produced gonna be also more reliable. The structure I'm gonna produce gonna be with two pitches value, as I said before, and both, as I said before, one-dimensional and two-dimensional. Among the technique that can be used to produce this kind of structure, here in FBK, we have electron beam lithography and focus ion beam, that are 2 nanofabrication technique. The electron beam lithography can be similar, let's say, to photolithography because of the using of a resist that then is developed and exposed by an electron beam. And thanks to liftoff, we are able to produce the metal nanostructure. By contrary, focus ion beam doesn't require any resist, but the ion beam is directly focused on the target, in my case, silver layer. And thanks to the energy that the ions are gonna bring with them, we are able to remove and therefore sputter the atom from silver layer. Because of the high aspect ratio of the slit and the low dimension of the slit that we need to fabricate, in my case, I decided to work with focus ion beam. And also because if we try to produce the same structure with electron beam lithography, and the resist collapse under its own weight before the metal liftoff. So just an overview of the equipment that we have here in FBK. We have a Vilium by Wraith company that has an eutectic liquid alloy of gold, silicon, germanium as source, that this beam is perpendicular to the target. And then also inside the same equipment, we have also an electron beam that can perform both some images and electron beam lithography. For those of you that are not familiar with this technique, we have the main working principle that we have an incident ion beam that is focused and accelerated directly on the sample. So in my case, the diode with over on the top, the silver layer. And as I said before, thanks to the energy that the ion bring, they are able to remove material from the substrate, so from silver. So we are able to remove, to sputter atoms. For this reason, one of the main parameters that we need to know is the sputtering yield, that is the number of sputtered atoms over the number of incident ions. Among all the side phenomena that can occur during this patterning, the main one that I'm more concerning about is the implantation of ions, because the implanted ions could affect the electrical behavior of the photodetector below the silver layer, because it can cause the trapping of electron hole pairs generated by the incident photon. For this reason, before starting the production, we evaluate the theoretical collision cascade of gold ions inside the silver layer from Monte Carlo simulation. And as you can see, the collision cascade is very close to an ideal configuration of, so very close to a box shape. And also the theoretical sputtering is around 15. This value is necessary to start an optimization of the process. So after the optimization of the geometrical parameter of the structure, and after the optimization of the nanofabrication techniques of the focus ion beam sputtering, I produced these 4 different configurations directly on a detector. So the slide is organized as follows. We have on the first row the lower periodicity, both one-dimensional and two-dimensional nanoarrays. And on the second row, we have the lower periodicity, so 260 nanometer, so both as before, one-dimensional and two-dimensional. As I said before, all the 4 configurations present a metal thickness of 110 nanometers. And as is clear from the results, the grating with the lower periodicity presents a low reliability, mainly because the ratio between the slit dimension and the periodicity is higher. On the other hand, the grating with the higher periodicity present a very good reliability, also dimensional conformity, and also in shape in the case of two-dimensional. So as I said before, the main concern of using this technique of active device is the fact that we are removing material with a gold ion beam directly from a device that can be damaged. For that reason, to be sure that the detector still works, we can evaluate what's so-called dark current density. That is also called noise in this case. That is just the current flowing inside the device under no illumination. If the diode is still working, we have that the dark current density is at least 3 orders of magnitude less than the working current density. That's in our case is in the order of tens of nanometer per millimeter square. Indeed, as you can see, a reference diode, that is a diode without any plasmonic structure on top, presents a dark current density of 21 picoampere per millimeter square. So I measured this dark current density for all 4 configuration at a reverse bias of 2 volts, and here are the results. And as you can see, for all 4 configuration, we have a dark current density in the same order of magnitude of the reference one, and well below the working current density. It means that we are able to pattern 100 nanometer of silver without implant too many ions gold inside the device to damage irreversibility in a way, irreversibility way, the diode below. This results is a very successful integration of metallic plasmonic nanostructure directly on an active device. And this result can pave the way to further integration both of plasmonic or photonic structure directly on top of a silicon photodetector. And one example could be a plasmonic biosensor all-in-one that we are currently work on, because this plasmonic biosensor all-in-one can permit us to have the sensing biosensor, so the plasmonic part, but also the detection part, all in one sensor, without using any Raman scattering or any optical measurements. So thank you a lot for your attention. If you have any question, please ask me. And for further collaboration, here are my contacts. And thank you, everybody.
Thanks, Elia, for the very nice presentation. As usual, our digital plus. And so do we have questions? Don't see any. I have. So I was curious about this. So you showed that the periodicity was in the two cases 260 and 530 nanometers.
Yes.
So basically one is double the other.
Yes.
Let's say that 10 nanometers is maybe a kind of noise in the measurements.
Yeah, also because here are a lot of simulation, but of course we have sensitivity, let's say, called that way.
Yeah, it's a kind of digital image, right?
Yeah.
So any clues regarding the fact that one is double the other? So since that the kind of periodicity is doubled, and so maybe it is the same.
Yeah, no, we know why, because it's based on physical phenomena. The nature of the gain between 500 of these two periodicity, I mean, the physical nature is different. In the case of the higher periodicity, we have the spectral matching of phonoresonance and other optical resonance. In the other case, on the 260 nanometer, we have just, let's say, diffraction resonance. So one is the double of the other one, because both are based on optical diffraction. But in one case, we have also some plasmonic phenomena and the other photonic resonance. So we know that we evaluate also the electrical fields for each configuration to know the nature of this gain. And probably if we extend the periodicity, the investigated periodicity, we have another pitch at the double of 530 nanometer, that is around 1100.
Mm-hmm.
But probably also the gain will be lower. For that reason, we didn't study.
Okay.
So everything stay in the nature of the peak. Sorry for the confused answer.
No. That's perfect. Very interesting. Very interesting. Yeah. Okay, I see that unfortunately we're running out of time, so we have to switch to our next presentation. So Elia, thanks again, and congratulations for the interesting presentation. So our next speaker is, beg your pardon if my pronunciation is not perfect, Obiora Adugu.
Yeah, no problem.
And yes, and talk will be about the investigation of thermal comfort and air quality in typical student residences. Please, floor is yours.
Thank you for the introduction. My name is Obiora Adugu, and I'm a graduate student of the Department of Mechanical Engineering and a member of the Applied Renewable and Sustainable Energy Research Group, also at the Department of Mechanical Engineering. And then today I'll be presenting I'll be giving the presentation on the investigation of indoor thermal comfort and air quality in typical student residences. Yeah, and so acceptable indoor air quality, is defined as the air condition to which there are no expression of discomfort and in which there are no likelihood of contaminants being above the stipulated standard as defined by ASHRAE and the WHO. 90% of our lives we spend indoors, and then according to research, indoor pollution is about 2 to 5 times that of outdoor pollution. So actually, this is a serious problem over the years. And this problem has in fact been impacted by COVID-19, which we all experienced the lockdown last year. And even if ventilation systems have improved and the cost of effective devices to monitor these indoor air pollutants have also improved over the years, we still find ourselves being plagued by this by indoor air pollution. Yeah, and so what we decided to do as a research group is for countries like Nigeria, countries that are underdeveloped and countries that are still developing, it's not so easy to measure these pollutants and to estimate the thermal comfort of individuals. And this condition is even more prevalent where students are involved, right? So most of you will find yourself living in places where there are air conditioned, but in student residencies, there are no such environments for them. Mostly it is naturally ventilated, and most of the time the population in there are way over the stipulated population. And so we decided to measure some of the indoor air pollutants and present it to structural engineers and architects for them to make decisions on how they construct these buildings, right? And we then went ahead to measure things like airborne particles, like the different particulate matter, household odors and gases, and the different VOC, the volatile organic compounds, and within going to molds and bacteria. And like I said, the issue of air quality would probably have been swept aside, if not for the fact that we spend 90% of our lives indoors, and this has well been aggravated by COVID-19. The EPA said that ensuring proper ventilation with outdoor air can help reduce SARS-CoV-2. As you can see on the slide, 10% outdoor air, 90% indoor air. This is really a serious matter. So aside from indoor air quality, we also investigated thermal comfort. Thermal comfort is also a prevailing issue. And the concept of thermal comfort addresses an individual relationship with their indoor environment. So how do they perceive their indoor environment? Different people, so the temperature indoor can be, say, 30 degrees, and you have two different people, and one of them is comfortable, the other is feeling very uncomfortable. And we went in depth to investigating this. And in terms of thermal comfort, there are actually two main things that affect, two main subgroup. One of the subgroup is dealing with the environmental conditions, temperature, humidity, air quality. And the other group is sort of dealing with the type of clothing the person is putting and the metabolic rates. As you can see on the chart here, we have the kind of clothing is putting, the humidity level indoor, the airspeed, the temperature, the so-called ambient temperature, and the metabolic rate also. So the methodology that we use, since this is more like a two-part study, right? So for the air quality, we conducted a survey of 120 student residencies with an on-the-spot detector. So the sensor in the detector and measured particulate matter PM 2.5, 1.0, and 10. And we also measured them HCHO, and then other gases which surprisingly came out to be 0. And 6 major residencies around the school area which is the University of Nigeria, were selected. 20 rooms in that location were surveyed, and the sample rooms are shown by the side. And then the measuring device were calibrated at first for 5 minutes, and it was brought indoor, and then the recording was taken for about 10 minutes, and while standing still. So you can see this is actually the instrument we use to measure it, and on screen you can see the various gases that we measured: HCHO, TVOC, the different particulate matters, temperature, the humidity. For thermal comfort, what we did, we selected 10 student residencies, and the reason why we picked them was because we kept the device there for about 8 hours, and 10 a.m. to 6 p.m. in the evening, and because from the ASHRAE standard, you need a certain level of hours for you to properly log and estimate the thermal comfort of students within that room. And we also measure the clothing and metabolic activities of this occupant at various times within that house. So after doing this, we took the results and a lot of data, and then we tried to group these results into 2 sets. So those residencies that were owned by the schools, that's officially owned by the school, and those residencies that are privately owned, so that we could see that relationship between them, right? So if you can see on the table here, you have different hostels with their name, the hostel type, if they are female-based or male-based, the different activities that the students were currently undergoing, and the ventilation, we left that natural ventilation, since 100% of the officially owned residences by the school were naturally ventilated. Yeah. So an interesting result that started to come out from this research was we started to see that for air quality, residencies owned by the school were seeing better air quality as compared to those owned by private individuals. And this is as a result of the set rules in the school hostels, right? So the school hostels do not allow activities such as smoking, and they don't allow activities like burning of bushes. They don't allow activities like cooking with combustible fuels. But outside the hostels officially owned by the school, those are there are no such set rules, and those activities are actually allowed. And you will see on my screen that when we compared this data with the ASHRAE standard, and then for air quality in particular with the WHO standard, one of the residencies and in Giorgio, the graph at the top, the 20 rooms that were surveyed were well below the set standard by WHO, which is 25 micrograms per meter cube. And the residencies owned by the private individuals, which is Hilltop as a reference here, most of the rooms surveyed were quite high in terms of pollution for PM 2.5. Then you can also see here for the indoor HCHO a similar result, not so similar in terms of Giorgio being way below the stipulated standard for sensory, and then the hostels owned by the private individuals and almost getting to that level of 0.1. When it came to thermal comfort, we decided to compare the results we had with ASHRAE standards, and then we used the CBA thermal comfort to develop by Professor Skivion by Professor Skivion. And then if you look at this chart on my screen, there are 8 residencies as indicated at the start of this presentation. The first three residencies, actually the first 4 are owned by the school, and the last 4 is owned by private individuals. And from the results showing on screen, you see that the first 3 are way above the thermal comfort level set by ASHRAE. And then this is also an interesting result. While the air quality, the ones owned by the school were good, those owned by private individuals were bad. When it came to thermal comfort, the residencies owned by the school were above the stipulated standard, and those owned by private individuals were within that stipulated standard. And this is as a result of the number of students being inside those rooms exceeded the amount of students that the school set initially when the building were developed. So in a particular room, 4 students are supposed to be living together officially, but on average, there are about 8 students in a room. And in some cases, you get up to 11 students in a room due to some financial issues. Surprisingly, Hostel 4, Peter Odili, was just right at the tip of the 80% acceptable limit. And then if you look at the situations at Peter Odili, most of the students there are PhD students, graduate students, and not undergraduates. And there are set rules in terms of living standard and the rest of them. Yeah, so with that, I come to the end of my presentation.
Thanks, Biora, for the very nice presentation. As usual, our applause for this. So, do we have questions? Don't see hands raised, so I think we have time for one. I will ask. Juan Obiora, still there?
Yes.
Yeah. Okay. So, so my curiosity is this. So basically, you made measurements, right? And
yes.
So the idea was to try to monitor the quality of living of the students. Okay.
Yes.
So out of that, what did you obtain?
Yeah. So what? Okay.
So because out of a monitoring system, so basically you need to provide some kind of so ideas or so plans to improve that.
Yes, and so out of what we did, measuring both the air quality and thermal comfort, we found that most of the students were living below a recommended standard for living conditions in the school areas. And then, so what we then did was to suggest to the school community, the school administration, that, okay, look, they need to be set rules for students living outside of the school that are owned by the private individuals in terms of smoking, in terms of burning of bushes, and using of combustible fuels. And for students living within the community, we suggested to the school that, okay, and the number of hostels available to students are quite small compared to the number of students available in the school. And then, so what the school is currently doing is building up new hostels, and beside the current one, they are partnering with private individuals to, build up more hostels to accommodate more students, and bring down the cost of those hostels, so people don't pack themselves together in a single room where we have 11 students instead of 4 students.
Okay. Thanks. I got it. Okay. Well, in that case, thanks again for the presentation. And so we are perfect on time, and so we can move to our next speaker, who is Aditya Parpe. And his talk is regarding surface mounted smart PZT sensors for monitoring damage using EMI-based multi-sensing technique. So Aditya, please, floor is yours.
Hello, this is Aditya from Indian Institute of Technology, Bhubaneshwar, India. When presenting the research work surface-mounted smart PZT sensors for monitoring damage using EMI-based multi-sensing technique in the 8th International Electronic Conference on Sensors and Applications. So firstly, the need of structure health monitoring is the motivation of our work, and it is been done to avoid the sudden failure and some maintenance problem. And in this particular field, we have been focusing on smart material named lead zirconate titanate, because it has a special property that it can act as an actuator as well as sensor. And utilizing this PZT patch, we are focusing on the EMI technique, which will be helpful for our work. And in this particular research, we have proposed the idea of multi-sensing technique on the surface-mounted PZT sensors, where we'll be discussing about the effective methodologies to monitor the damage in the concrete structure with the help of surface-mounted PZT sensors. And also, we'll be covering the important aspects of SHM, that is the damage detection and damage localization. So firstly, let's see the methodology for the damage detection studies. So initially what we are doing, we are assuming that sensors are harmonically excited in the high frequency range. And as a result of input voltage, we'll be obtaining some conductance signatures at different stages. And to compare them, we'll draw some metrics like statistical metrics, namely as root mean square deviation and correlation coefficient. And it has been done to see the better understanding of the signatures. Whereas for the damage localization, we are assuming that the group of sensors are to be in parallel connection, and we'll name those particular group of sensors as a combination. And this multi-input single output mode is preferred because we need to obtain some composite signatures of those particular combinations. And in this particular studies, we have considered 3 combinations, that is SSU23, SSU13, and SSU123. And with the help of the composite signatures obtained from this combination, we'll be evaluating dynamic metrics, namely moving RMSD and moving CC, which will be helpful for the localization of a damage. And in those plots, we'll be focusing on the magnitude of this moving RMSD and moving CC. So let's start from the numerical investigation work, and we'll introduce the smart sensing units, which is a combination of steel plate plus adhesive layer and PZT patch. In our particular research, we have used the material PIC151 for PZT patch, and these SSUs are harmonically excited in the particular frequency range, that is 0 to 450 kilohertz. And as a result of this harmonically excitance, we obtained some composite signatures. And since these SSUs are having different thickness of steel plates as a result of the EMI technique, we come to know that the resonant frequencies of these SSUs are different from each other, which states that all these three sensors are different from each other, and we will be requiring this data given in the table in the upcoming few slides. So the next step was to paste these SSUs onto the top surface of concrete beam for the damage monitoring. So we incorporated the crack of length 20 mm, and also we introduced the influence of external cases, that is 10 kilonewton and 30 kilonewton. And from the figure and from the table as well, it is clear that the SSU2 is nearby to the load location and SSU1 is nearby to the crack location. Accordingly, these SSUs are harmonically excited and load conditions were given to our FE model of concrete beam, and as a result we obtained some conductance signatures from these SSUs at different stages. Coming to the result part from this particular numerical investigation, we obtained conductance signatures from SSU1, SSU2, and SSU3. So out of these three figures, we come to note that in the first figure, that is for the SSU1, it is the only sensor which was able to detect some changes in the conductance signatures due to the presence of damage, whereas the conductance signatures for SSU2 and SSU3, they notice no change. It seems that the SSU2 and SSU3 are kind of insensitive of damage inclusion. So from these particular three curves, we come to know that the SSU1 was the only sensor which was able to detect the presence of a damage, and that is how we detected the presence of damage from these particular studies. Now our next goal was to localize this damage. So I mean, before localizing, we also used some statistical metrics, that is root mean square deviation and correlation coefficient, and they also predicted the same story, that SSU1 was the only sensor which was able to detect the presence of the crack location. So as of now, we discuss about the damage detection study. Now the next work is to localize this damage. So as I discussed earlier, that we'll be assuming that group of sensors are in parallel connection, and accordingly that can be sensed as a combination. So this sensors are assumed to be in combination, and due to this presence of combination, we'll be obtaining some composite signatures. And from those composite signatures, we'll be evaluating dynamic metrics. And out of them, one of is moving RMSD. So here we have plotted 3 moving RMSD plots for combination SSU23, SSU13, and SSU123. So in first figure, if we will be focusing for the magnitude of moving RMSD nearby the resonant frequency of respective sensors. So if we see the first figure, it is clear that the magnitude of moving RMSD is higher at the resonant frequency of SSU2, that is 350 kilohertz, than the SSU3, that is the 355 kilohertz. And the same trend was observed in the second figure, where we come to know that the magnitude of this moving RMSD is higher at the resonant frequency of SSU1, that is 335 kilohertz, than the SSU3, which was the 355 kilohertz. So from these three figures, it is clear that neither the load location nor the damage location is nearby to SSU3. And from the damage detection study, we come to know that the SSU1 was the only sensor which was able to detect the presence of a damage. So therefore, from these studies, we can infer that the crack location is somewhere nearby to SSU1. And that is how we, we can also verify this inference from the given table which was given in the previous slide, and it was also saying that the crack location was somewhere nearby to SSU1. So with the help of this studies, the data is verified. But to validate this data, we have evaluated another dynamic metric, that is moving CC. So again, these moving CC plots are evaluated from the composite signatures of those particular combinations, and the same inferences have been made. Like if I see the figure first, that is drawn for the SSU23, it has come to know that the magnitude of moving CC is lower at the resonance frequency of SSU2, then SSU3. And in figure B, it is come to know that the magnitude of moving CC is lower at the SSU1 than SSU3. So again, the same inference is made here that neither the load location nor crack location is nearby to SSU3. And it has been confirmed that the crack location is somewhere nearby to the location of SSU1. But so up to now, the numerical investigations have been performed successfully, but we need to validate it from the experimental work. So we'll be validating this numerical work with the experimental work done by the Wang et al. In 2013. They have taken a plain concrete beam of given size, and they also pasted this similar PZT sensors on the top surface of concrete beam. And they considered two different damage locations. In case one, they considered a 10 mm long crack at location A, and in second case, they considered a 28 mm long crack at location B. And for better understanding, I have put it down a table which shows that the PZT1 is nearby to the location of crack 1, and PZT2 is nearby to the location of crack 2. Accordingly, these sensors are also harmonically excited in a particular frequency range, and will be evaluating conductive signatures. So here are the conductance signatures which are obtained from these PZT sensors, and it is come to know that in figure A, that PZT1 was the only sensor which was able to detect the presence of 10 mm crack, because it was the only sensor which can only sense the changes caused in the conductance signatures due to the presence of 10 mm crack, whereas PZT2 was the only sensor which was able to detect the presence of 28 mm crack. But here, if you see the plot for the PZT3, that it was neither able to, it was not able to identify the presence of neither the 10 mm crack nor the 28 mm crack. So that is how we validated our damage detection study from the experimental work. And we also evaluated the statistical data, that is RMSD and CC. And it also says the same thing, that PZT1 was able to detect the presence of 10 mm crack, and PZT2 was able to detect the presence of 28 mm crack. So as a part of conclusion, I can say that the trend of experimental results shows a good correlation with the numerical results, and also the surface mounted SSUs are working well in the complex thing like concrete also. And our novel idea of multi-sensing technique on the surface mounted PZT sensor can be recommended for effective SHM, because it is considering the important aspects of damage detection and localization, and accordingly these studies have been performed successfully in numerical and experimental way. And thank you for your kind attention. If you have got any questions, please ask.
Thanks, Aditya. Unfortunately, we're running out of time, so we don't have time for questions. Let's move to our next speaker, who is Niharika Gogoi. And she is going to deliver this presentation concerning install gate acquisition system based on wearable sensors. So please, Niharika, floor is yours.
Hello, everyone. I'm Niharika Gogoi, and I'm a PhD student of FAO Erlangen. And today I would deliver my talk on install gate acquisition system based on wearable sensors. So this is the agenda of my talk. So I'll give an introduction about GATE or GIAT and my project team and methodology, where I talk about the sensors I have used, the structure design, and data acquisition. And next is results and discussion, where I would discuss about the results that I got from the different sensors. And then I'll have the concluding remarks. So what is GATE or GIAT? GATE is actually graphical representation of motion of animal or human. But in our work, we basically prefer or we study human gait. So human gait actually means how we figure out the movement of human beings, like by whether he's running or walking or any kind of human motion. And why we measure it? Because we want to know about the condition of the human muscles or also the mechanics itself. And there are two methods of human gait analysis. One is video and image capture, where various optical setups are used where the videos and images are captured, and then via image processing, their motion is like detected and then analyzed. And next one is sensor based, which is like wearable and non-wearable both. And wearable means something that you fix it into your body parts and there is like no restrictions, you can just move around. And the next one is non-wearable, which is fixed to a particular research laboratory or maybe in the doctor's clinic. And then like you can just do the sensing, but it's just fixed to one place. And in our work, we are going to discuss about the wearable sensors and how is it beneficial. It is beneficial for prevention, treatment, diagnosis of diseases, sports training, and rehabilitation. And regarding the project team of my work, in my work, we decide to put the sensors on the footwear or a shoe insole, and we choose piezo sensors and IMUs, which are low cost and wearable sensor. And the arrangement is such that we use array of sensor modules at different points of the shoe sole. And basically the objective is that we want to do multiple sensing at the same time and at the same measurement point. And also we want to get the pressure map under the feet and the orientation and acceleration of the feet. And coming to the methodology part, I discussed briefly about the sensors I have used. So I have used piezo sensors from Murata Electronics, and which is this is the code, and this is 12 millimeter diameter, and its resonant frequency is 9 kilohertz. And basically this sensor senses the pressure and then converts to electrical signals. So it helps us to give us pressure distribution under the feet when we see from the perspective of gait analysis. And next is inertial measurement unit or IMU, where you have accelerometers, gyroscope, and even magnetometers at point. And for our work, we use BMI 270 from Bosch Sensors. And this BMI has accelerometer and gyroscope with 3 axes, X, Y, and Z. And from the perspective of gait analysis, this accelerometer helps to give us the change of velocity of the feet, and this gyroscope tells about the orientation or the posture of the feet by measuring its angular rate. So this is the structure, and we put our left foot, and we put this sensor at 3 points, like the sensor module. So we put it on the toe, metatarsal, and heel. And each of these sensor modules looks like a structure, something like this, where we put the IMU on a PCB board like this here, and then the piezo here. So whenever you're walking and you're striking the ground, there is a force acted here, and then the PZT senses and generates signals. So the final structure looks something like this, which is made of aluminum. And the electrical connections or the PCB in which we place the IMU is this one, which is designed in Altium. And this is the electrical connections that is involved in this whole sensor module. So basically we use 3 sensors at 3 different points of the left foot. And to conduct the experiment, we do 10 steps, which means 5 steps for each foot. And this is the methodology part or data acquisition part, where we use multiple sensors, like we have 3 IMUs and 3 PZTs. And for that, for multiple IMU sensing, we use multiplexer. And then for multiple piezo sensors, we use ADC. And this multiplexer and ADC is connected to the Arduino through I2C interface. And then we use SD card through SPI interface to store the data. So basically we use Arduino Duo here, which does 2 tasks, that is writing the data, acquiring the data, and also saving the data on the SD card. And however, the simultaneous reading and storing of the accurate data limits the sampling rate of this whole setup. Now we come to the result and discussion part. And here you can see that I take the diet of 3 individuals, and the information about individual is written here, like the age and the weight. So in each of them, you can see that we have acquired 3 signals, that is from the toe, metatarsal, and heel. And for each of the cases, you can see that the metatarsal signal, the blue one, has 5 peaks. And that's what represents the 5 steps, what we considered in our experiment. And if you see the first one, you can see that this person walks mainly putting pressure on the toe and metatarsal and not on the heel. And this is what is human gait analysis about. Like when you put it on the footwear, it's not the same for every individual. Like each one of us has a different pressure map under our feet. And coming to the discussions about this result is that every individual has a unique gyre pattern, and this peak occurs when your feet strikes the ground or when there is some pressure you generate on the sensor module. And you can see that the nature of the peak varies for each individual, and it depends on the pressure being exerted, also the weight of the person, and the pronation while walking, and the walking speed. And if you observe clearly, the metatarsal is the most impacted point on the feet. And this is another interesting result where we saw that the piezo signals from the same individual actually changes, and it's like the same pattern we tried to follow, but it just changed for the same person. And probably this is known as intra-individual variation, and which occurs in our daily situations, and this is what makes the regular health monitoring a bit complicated also to access, but it's very interesting because it varies with time and circumstances. And the next important part is the sensor module, how we relate the signals from each sensor. And here, if you remember, I've told that I put 3 sensors at 3 points, and now I discuss about the one at the metatarsal. So this is the one from the piezo, and these are the 2 from the IMU. So this gives the acceleration data, and this gives the gyroscope data. And here I have tried to distinguish with gray points and black points, where gray points tell about the ground strike and the black point tells about when the feet is lifted. And this is what is from the piezo. And for the accelerometer data, I just want to tell that we place the accelerometer in this direction, and we consider our foot or the shoe in this direction. So this is X, this is Y, and this is Z. And depending on the consideration of these 3 axes, you can see that each axis give us some information about each part. For accelerometer, you can see that in the X direction, they tell us about the forward movement, and Y is the pronation, because every individual tries to lengthen their feet either inward or outward across the Y axis. And the Z is, of course, the lifting of the feet. And for the gyroscope, you can see that it tells about the rolling or the angular variation of the feet. So for the X, it can tell you about the inward or the outward landing, which is again related to pronation. And for Y, it's mostly the rolling of the feet. And for Z, it's usually least affected because it's not so much of significance when we don't roll it much on the Z direction, and which is very obvious. But however, one thing is to be considered, that the sampling rate of both the types of sensors are different because they are different sensors. And this is slightly brings a little bit of time shift in all the segments. So that was all. And now I reach the conclusion. So basically, I talked about my work where I designed a shoe layout with 3 sensor modules at 3 points of the shoe sole. And from our understanding, we see that the metatarsal is the most impacted point of the feet, irrespective of the walking pattern. And the gyre is always affected by walking speed, pressure, and pronation. And from the piezo sensors, we can get the high and low pressure regions, and that's how we get the pressure map under the feet. And for the IMU, we get projection and orientation of the feet. And in the next step, we would like to correlate the behavior of both the sensors and extract clinical information from the signals. So that was all. And thank you for your kind attention. And I'm happy to answer any questions or receive any comments from any of you.
Thanks. Thanks, Niharika, for a very interesting presentation. So as usual, how applause for you. Do we have any questions? Elia, please. Yes.
Sorry, still me. Yeah, very interesting.
You're welcome. You're welcome.
Thank you.
I have a question. I mean, in your opinion, do you think that this approach can help also maybe for people with disability to improve also the how they walk, or maybe for runner or whatever sportive people? I mean, I mean, in my opinion, the more interesting field to apply this is this two. What do you think about that?
Yeah, so first thing is that we choose shoe, and for that the healthy and unhealthy, both of them work, like wears it. So it's important for all kinds of people. And next is, of course, it helps because I read that in the pressure map, like if this is your feet and this is the pressure map, it actually varies depending on your illness. Suppose somebody had a stroke or he is paralyzed, so his walking skills are always different, so he will just limp. And when he's trying to improve his posture or improve his walking, then this sensing and this gyre monitoring is really helpful. And it is also helpful if you're having fractures in your ankle and you're improving your walking pattern. And also for the sports, I think accelerometers are very important for the athletes, especially when they are trying to speed up their running process, or how much leg they have to lift when they are doing some high jump or something. So these accelerometers and IMUs will be more useful. But pressure maps will be more useful for the unhealthy or stroke, for rehabilitation, and the neurological problem maybe.
Okay, thank you so much. Very clear.
Thanks. Thanks, Elia. I was about to ask exactly the same. And so the problem of disability or maybe of elderly people is obviously important in case you have to do this kind of analysis. We have a question from the audience, and Akhilesh Kumar asks, so if so sensor, they generate different types of data for people having different weights. So can you handle this? So and maybe I try to integrate with my question. So do you plan to have a deeper data analytics in order to do sensor fusion, put everything together, and having the capability to distinguish what's maybe related to a disability, to a illness, or something regarding instead habits maybe of the person, or in this case assess the weight?
Yes, I think weight is one of the factors, but it's not the only factor. And because I already told, like there are a lot of healthy people who don't put a lot of pressure on the foot, and everybody's pressure points are different. So somebody walks like this, somebody starts their walk with heel. So that's the pattern of gyre or pattern of walking that an individual have. And the next thing, so that's the reason why weight is not the only thing. And the next thing is that I'm going to increase the number of sample size with more people. So far I have only done with healthy, but I'm going to try with a lot of maybe with different age groups of people to get a more accurate signals or data and observe it, how it changes with each one of them.
Okay, very, very nice, very interesting, very good. So, Niharika, thanks again for the very interesting presentation. And so now it's time to move to our last speaker. who is Gianluca Mezzanzanica, and was going to present his contribution towards a multi-interdigital transducer configuration to combine focusing and trapping of microparticles within a microfluidic platform, a three-dimensional numerical analysis. So Gianluca, please, floor is yours.
Okay, thank you, Professor Mariani, for the presentation. So good morning, everyone. I'm Gianluca Mezzanzanica, graduate in Materials Engineering and Nanotechnology at Politecnico di Milano. And I would like to present you the work related to a versatile microfluidic solution for microparticles trapping and focusing, exploiting the acoustic manipulation of particles. That was realized in collaboration with the Université Gustave Eiffel and Professor Olivier Francet. So the background of the problem is related to microfluidics, which is the science dealing with the processing of small amounts of fluid, and the lab-on-chip technology exploiting microfluidics to implement on the same platform different biological and medical analysis. One or more actions in biological analysis can require the isolation, the focusing, or the separation of particles with different physical properties. And one innovative biocompatible and non-contact solution to overcome all these issues is the acoustic manipulation technique. The acoustophoresis is the phenomenon related to the use of ultrasound waves in a fluid to develop acoustic radiation forces, which can move microparticles. The specific kind of devices studied in this work exploit surface acoustic waves generated through interdigital transducers, which are deposited on the surface of a piezoelectric substrate. This technique can be exploited, for example, dealing with blood to manipulate red blood cells and study blood diseases. So the aim of this analysis was to study a configuration composed by 4 IDTs to achieve a versatile manipulation of particles and cells in a microchannel. So the working principle of a SAW-based device is described in this slide. An AC signal must be applied to the electrodes composing the interdigital transducers. The electrical input is converted through the converse piezoelectric effect in a mechanical response of the substrate, on the surface of which traveling surface acoustic waves are generated. When 2 or more counter-propagating waves constructively interfere, a standing surface wave is developed, and in this wave, a standing pressure field composed by fixed pressure nodes corresponding to 0 amplitude of the pressure wave and antinodes, where the maximum amplitude, for the maximum amplitude of the wave, is transmitted to the fluid contained in a microchannel. Depending on the physical properties of the particles, they can be displaced towards these pressure wave nodes or antinodes. So therefore, microparticles can be manipulated by adjusting the interaction between the surface acoustic wave and generating a precise pressure distribution within the fluid. So the numerical model was developed using Compson multiphysics. The piezoelectric effect on the substrate is achieved by coupling the electrostatic and the mechanical fields through the piezoelectric constitutive law. The acoustic pressure field is governed by the Helmholtz equation, and the particles are subjected to 2 cooperating forces, which are the acoustic radiation force and the fluid drag force, transporting the particles. So in the slide, the geometry of a simple device is reported in gray. The device is composed by a lithium niobate substrate, a PDMS microchannel, and 2 facing IDTs. The animation shows the propagation and the interaction between 2 counter-propagating waves, finally resulting in a standing surface wave. The top right plot reports the trajectories of the particles, which are transported by the flow of the fluid and are focused on the central pressure node by the acoustic radiation force when they interact with the pressure field. So therefore, the focusing effect on particles was demonstrated and can be achieved only using 2 IDTs. So the blue and the red parts are related to the pressure field that is developed inside the microchannel, the fluid in the microchannel. Therefore, to improve the focusing effect and to achieve also the isolation of single particles, a configuration made of 4 IDTs was analyzed. The aim is to increase the versatility of the device, having the possibility to change the microchannel geometry to exploit the wanted effect on particles. The platform is made of a square section lithium niobate substrate, above which 4 gold IDTs are deposited, tilted by 45 degrees with respect to the X direction of the 3D reference system, and a PDMS microstructure placed in the region between the transducers. In order to investigate the versatility of this platform, 2 PDMS structures have been modeled. So first, a straight microchannel containing flowing water to achieve the focusing effect on particles dragged by the fluid, and then a squared-based chamber containing static water and particles to achieve the trapping effect. So in the table are reported all the parameters of the geometry of the system, and as you can see, we are in the range of maximum some millimeters for a whole platform. So in order to investigate the interaction between 4 traveling surface acoustic waves, this other configuration was modeled. With this solution, the waves are constrained to move along the 4 directions and to interact in the central region. In the image, the surface displacements are plotted as in the out-of-plane directions, and the 4 waves constantly interfere in the central region of the platform, generating a standing surface acoustic wave, which is characterized by a regular distribution of nodes, which are the green regions in the plot, and antinodes, the blue and red regions of the plot. It can be difficult to achieve the wanted wave pattern due to the interferences which are generated by the wave's reflection at the boundaries of the device. So to avoid them, the low reflecting boundary condition was applied to hold the lateral boundaries of the device. And the same solution can be obtained in real device by attaching absorbing material to the boundaries, so avoiding the reflection of the waves and the interferences that can develop. So the same wave pattern is transmitted to the fluid containing to the PDMS structures, which is positioned above the piezoelectric substrate, and the waves are transferred to the fluid in the form of standing pressure waves. The 2 modeled structures are reported in the plots, and the red and blue colors are associated to the maximum and minimum values of the pressure, such as the antinodes, while the transparent regions are the nodes where the pressure magnitude is 0. The results reported are in a steady-state condition because are obtained as solution of a frequency domain analysis which was performed. So this pressure field is implemented then into the numerical model in order to compute the acoustic radiation force which can act to the particles to displace them and control their position. Therefore, the reported configuration with the straight microchannel can be exploited for particles focusing. So polystyrene spherical particles with a diameter of 8 micrometers are used. And in the image, you can see that the trajectory of the particles, which are the colored lines, are dragged by the fluid into the PDMS channel and are plotted. So the focusing effect is demonstrated. So the particles are dragged by the fluid flow and moved. And when they move, interacting with the pressure field, that focus on the pressure nodes that you can see in the plot. The same result was achieved only using 2 IDTs, as was reported in the initial slides. And as can be seen, the particles are displaced by the acoustic radiation force from the pressure antinodes to be focused on the pressure nodes. By adapting the geometry of the channel, the particles can be focused and collected at separated outlets at the end of the channel. So the great advantage of this configuration with respect with the 2IDT configuration is the versatility. So as reported in this slide, different positions of the microchannel can be used to achieve different locations for the pressure nodes within the fluid domain. Therefore, the design of the PDMS microstructure is important to generate a specific standing pressure field and focus the particles on the wanted direction. So by modifying the geometry of the channel and its position above the piezoelectric substrate, knowing the standing surface acoustic wave distribution, the location and the number of the pressure nodes can be selected. So this solution can be useful if you intend, for example, to sort cells at different outlets, depending on their physical properties, or can be exploited for particles focusing on a single line. So a phenomenon that can avoid the obstruction of microchannels, for example, when dealing with many particles, and so we avoid the obstruction. The same effect can be achieved by modifying the phase of the assist signal applied to the IDTs, and with this solution, the control of the particle motion can be enhanced a lot. So the analysis performed on the PDMS microchamber instead highlights the possibility to isolate the particles by trapping them into the pressure nodes of the distribution. So the animation shows the isolation of one particle, which continues to oscillate within the pressure node, being pushed laterally by the acoustic radiation force. And these effects last for 0.2 seconds, and then the particle is dragged inside the node and trapped. The solution demonstrates that the versatility of the platform, which can be exploited to achieve different results as cell sorting, focusing, or trapping. The trapping effect can be used to isolate single cells or to aggregate them in spheroids, which can be collected from the platform and then analyzed in a separate location. Also, if the phase of the acid signal on one IDT is modified, the same effect is produced on the phase of the surface wave. So the phase of the surface wave is changed, causing a modification to the standing surface acoustic wave pattern on the surface of the piezoelectric substrate, and therefore also the standing pressure wave inside the fluid is changed. By controlling the phase change, the particles can be manipulated and moved towards the wanted direction. So with this configuration, this effect can be exploited in 4 directions. So we can select in which direction the particle should be moved and controlled. Okay, so to conclude, the studied configurations can be considered as a low-cost integration to a lab-on-chip solution for microparticles manipulation. The versatility of the platform was demonstrated both in terms of effects like particles focusing or trapping, and the design of the microstructures. The future trends are related to this solution in the use in biomedical field to improve the efficiency of the diagnosis, for example, of tumors or diseases, by enhancing the accuracy of this analysis. So thank you for your attention.
Thanks, Gianluca, for the presentation, and as usual, our digital applause to you. Elia, I see you have a question, so please ask.
Sorry for this, but it's quite congratulations first for the presentation. Very interesting topic. That is quite funny because I attend the same engineer course in Politecnico of Milan. So, but yeah, I have a couple of questions. The first one: have you planned to fabricate this type of structure after your simulation? Maybe, I don't know, with other internship or I don't know.
Yes, the idea was to try to realize that when I was doing my one internship during my study in this university in France. So it was the Université Gustave Eiffel. The problem was that we had not time enough to construct this kind of a structure. So we have realized only one PDMS microchannel, so simply only the microchannel, but all the electronic part and the position of the interdigital transducers were not realized. But I found some interesting results also in literature that was confirming my simulations, so this was quite good.
If I may, I have another one.
Yeah.
Yes, please. And do you think that this kind of structure can also trap gas molecules or just in liquid phase?
Yeah, sorry. I don't know if it's possible to do it in the gas system simply because the effect is realized due to the use of surface acoustic waves. So dealing with gases is, I think that is not so easy to manipulate. Is in the same was with a fluid like water or a liquid fluid. Maybe it can be proved by other simulations or with some experiments that dealing with gases, it's like the same to produce a pressure wave inside a liquid, and so maybe the manipulation can be done. I don't know if it's possible to do it with at the molecular level because of the effect of the pressure wave is not so high to control molecules, I think, but with microparticles it works, and I think it's possible.
Okay, thank you. Congrats again.
Thank you.
Thanks for the very interesting discussion. So I think we are now at the end of our session. So Elena, maybe I can say a few words to conclude. So first of all, we have to thank all the students for participating in this session. Really, our big applause goes to you all. It was very nice, nice as usual to chair this student session as it was like last year, and really your contribution is so your contributions are very much appreciated. So thanks for being part of this Congress. This Congress, which is about to conclude in the sense that this is the last online session. and that doesn't mean that the Congress is ended at all, because so officially it is still open till November the 15th. So every one of you is welcome to go online, to read the contribution, to interact with the others, because you know that this is possible with the chat box that you have inside each single web page of the Sci Forum platform. And so please do it in order to make our conference a bit less electronic and be more physical. So even though in this kind of, say, pandemic area we are living, and so this is still a way of having this interaction to be of vital importance. So thanks again for this participation. Thanks to you all. And now I lend over to Elena for some final remarks.
Yes, only I wanted to thank you also, Stefano. I think we all agree that he deserves also a virtual applause to you, that you've been applauding everyone. And well, as I think you mentioned everything, just that the live session has been recorded, and we will post the recording soon at the conference webpage if you want to check it again. And I think that is all. So I wish you, we hope to see you in next events, next Sensor events. And I wish you all a good day, good evening, good afternoon, wherever you are in the world, and take care. I will close now.
Thanks. Bye-bye, everyone.
Bye-bye to everyone.
Bye.